Jeez, we are on. I mean, say hi. Say hi to the fucking camera. It's right there for you.
Woo.
Shout, scream.
You're getting me to
Skydive. Put
do
your hand,
things. Yeah.
put your hair on my shoulder. Excuse me.
Excuse me. Okay.
Alright. So I brought Amin as I promised because we want to see what's he doing. 4 years in PhD, 3 years in,
4 years in the 5th year.
and the 5th year.
Yes.
So it's the time for him to give his RQE for us. We
Well,
wanna evaluate.
RQ was a while ago, but okay. Well, it's not RQ, but you know, my research specifically.
Our subscribers and viewers will judge you.
That's okay.
We are the true feedback here.
Yeah. Well, the committee decides whether I get a PhD or not. But okay.
All right.
So, yes, my research broadly is applied machine learning and AI in mechanical engineering.
All right, bitch. Okay.
Yes.
It's just bragging. Applied machine learning.
It is applied machine learning because we don't do any theory on machine learning or really on mechanical side.
Dude, this is it. This is it. This is what we wanna hear in armchair theorists. They
Yeah.
do shit. They do it. They make it happen.
Yeah, I guess.
Alright.
I mean, we make some things happen. But
Alright.
yeah, so the basic thing is, so the way we do it is, we look at different AI methods that are out there and we try to see where it makes sense to apply to mechanical engineering design tasks. So, you know, a lot of times this is an optimization. A lot of times this is in some other form of like forward modeling.
What is the application of mechanical engineering? then?
Okay, we can talk about some basic mechanical engineering stuff, but basically anything that moves and any machine that you use any day in your life.
Like cars.
Like cars, you know, that's the that's the easiest one to go. It's like, oh, mechanical engineer, can you fix my car?
Motherfucker moves.
Yeah, airplanes, cars, you know, military obviously is the biggest industry, at least in the U.S. when it comes to mechanical engineering, because you know missiles, trucks, tanks, whatever, internal combustion engines, you name it, whatever.
Mm-hmm.
Like anything that is moving, anything, you know, electric motors, things like that.
Okay.
Anything that is also, well, not necessarily but moving, but manufacturing is also pretty much done by mechanical engineers.
And the design and
Well, design is a whole thing. So design is a whole field. It involves many different disciplines of engineering. Mechanical engineering is one of the disciplines involved in design.
What do you think about the design of Tesla? What do you think about mechanical engineers for Tesla truck?
So what, the Cybertruck?
Cybertruck, Tesla truck.
Yeah, I don't think that's the engineer's fault. It's a very shitty design. It's a garbage design. I mean, there's no reason for us to pretend that it's not a garbage design. It is a garbage. It looks like a fridge.
I think it was just
It's-
first 5 days. Okay, it is something exotic. And
Exactly.
now, if you are on the street, where
You look at it once and it's like, oh shit, this doesn't look like anything I've ever seen before.
Yeah.
But there's a reason this doesn't look like anything you've seen before because it kind of sucks. And the reasons why it's
Not everything that is like strange or like is
just
good.
because it's novel doesn't
Outstanding,
mean
yeah.
it's good.
Yeah.
It's creative. It's novel.
But
You
now
need creative and novel designs.
Yeah.
That's like a very important thing in design is creativity.
Mm-hmm.
But you also have to be aware of performance and practicality.
I think aesthetically it's not beautiful even.
To some people it may be, but there's ugly cars that come out of any manufacturer.
Mm-hmm.
Right. I think aesthetics, fashion is one of those examples. It's trends. There's different things that people like. So these days I don't really like the designs of cars because pretty much all the cars are starting to look alike. You know, with the angled designs and the LED strips, and they're all just becoming the same thing. Like they're morphing into like one design.
Is it
style.
because of the mechanical?
Like there
part?
used to be a time
For efficiency
where Mercedes
or-
had a unique Mercedes look.
Mhm.
Like you see a Mercedes and you're immediately going to, oh shit, that's a Mercedes.
Mhm.
Or BMW. It had those like two grills.
It still has, right?
Yeah, but they're barely noticeable now.
Uh,
Like everything else in the car is just so streamlined into a very specific design discipline.
mhm.
that you just kind of lose that creativity.
What is the specific design? Is the design for efficiency or for the from the?
No, this is all just like trends, right? Like aesthetic is aesthetic. Efficiency is different.
I see.
Efficiency will be pure engineering, right?
Mhm.
And or performance. Those are pure engineering. Pure
Yeah.
engineering is
Will it become very ugly? If you-
yeah. So if you really try to, so Mercedes did this experiment. There's a whole YouTube video on this
All right.
where they tried to make like the most aerodynamically,
Uh-huh.
efficient car.
Mm-hmm.
Just for context.
Is it like a missile?
No, that wouldn't be very efficient on the ground.
Okay.
Yeah, so if you try to, just for context,
Mm-hmm.
your car's fuel consumption
Mm-hmm.
is mostly, at least in highway, going to go to air resistance. That's the majority of where that fuel goes.
Oh, air.
Yeah, air resistance. Because rolling resistance it can be high if you have thick tires. The
Mhm.
rolling resistance can be
Yeah.
high. But compared to the air resistance at highway speed, it's not that big. So something like 50 to 60% of the energy consumption goes to the air resistance. So if you
Okay.
can reduce that by 10%, that's a lot less fuel usage, right? So people have been looking at aerodynamics, and then Mercedes did this thing where they tried to make the most aerodynamically efficient car, and they were like, well, you can technically make a machine that performs the task of a car that has very low aerodynamic drag, but it stops looking like a car.
It's not looking like a car.
Right, it starts looking like something else.
Mm-hmm.
And that's not a car you can sell to people. Like people,
Do we have a photo of it?
if you go to YouTube, I think we can find the video probably. Like somewhere. Yeah, let me just, I can
Let me
search it.
also. Wait.
Yeah.
Maybe also we bring ourselves. Yeah, we are in the corner. No
Yeah.
problem.
So, Mercedes. Okay, no, caps is on. Caps is still on.
Doesn't matter. It's just aesthetic.
Thanks. So there was a video.
Go to images, maybe.
No, it's like a. These are just advertisement videos.
These are advertisements.
Yeah, they will come up.
Well, they will look like
So it wasn't a
F1
Mercedes.
cars, right?
No.
No?
Oh, F1 cars have very different setup.
Mm.
Like F1 cars are not designed for human beings necessarily. They're designed to force single individual driver in there, and every single F1 car is tailored to the driver.
Mm-hmm,
So the dimensions of the driver,
oh,
they take that.
They
into account.
design
So,
for
yeah,
one person.
Yeah. So
Like Michael
Max
Schumacher.
Verstappen
Uh,
has his own measurements, and they make the
Mm.
car for him.
damn.
It's like a one-off. A lot of the technology in today's cars started out in F1
Mm-hmm.
because that's basically like if you're a pure engineer, that's your like favorite thing to do in the world. Like that's the best job you're ever gonna have, is to work on a F1 design
Personalized.
team. You work on an F1 design team because
Ah.
you can just like push every little bit of the performance in there. You can just like,
Ah.
oh, let me optimize the wheel bearing. Like you can go that deep, right? Because everything is about like the tiniest margins matter. So these days it's less about the driver, more about the engineering.
I see. Ah.
Yeah. So these days you see, okay, 1 year, one year you see Mercedes winning every single race almost.
Mm-hmm.
Apart from the accidents that happen. Like the
Damn,
Red Bulls.
that's great.
And then the next year you see Red Bull winning. Like this year I think it's Red Bull. Like they win all the races, most of the races. So
they got
pretty
the
much-
good engineers.
yeah, like pretty much like a few races into the season, everybody knows which team's gonna win. Like it's like this year they have the better car. That's it.
Dude, let me see the result of them. How is it?
You just type in
F1.
F1.
Damn, this is an engineering race. That's so beautiful.
Yeah, so if you're a
We don't
purist,
have it.
if you're a purist engineer,
Uh-huh.
then so Verstappen is first at the Red Bull team. Yeah, so I was right about the Red Bull being the
Mhm.
first right now.
But no, this second one is McLaren.
Yeah, but you see 7 wins and then the next one is 2 wins. It's like, yeah, it's like fucking, it's over.
Mhm.
Right? Like, this is the team that's going to win because they're winning basically every
But
race.
all of them is Verstappen.
Hmm?
Well, all of it is Verstappen.
Verstappen, yeah, the other. So
Is
this
it
how
the,
it works
is it
in
the
the teams.
only Red Bull?
You have a primary, no. You have
Okay.
multiple drivers. The primary driver will always, like, your secondary will always allow your primary to win.
Okay.
Yeah,
like
so they
kinda-
will always, yeah, it's like an agreed upon thing because if you have 2 drivers of the same team competing for winning, your team won't win.
Like here, look at this. We have Mercedes, but 2 people from
Yeah,
Mercedes.
Lewis Hamilton, it has 2 wins.
Okay.
But what I'm saying, you see the difference.
Yeah,
right?
difference is massive actually.
7 wins.
Uh-huh.
But McLaren is close because they have 10 podiums. Like they have second places and third places. They have 10 podiums as well.
What
So
is podium?
podium means 1, 2, 3. Like you get the prize. Like if you're top 3,
Uh-huh.
like gold, silver.
Ah, okay,
bronze.
okay.
Like they make the podium.
Who is the next Red Bull?
Red Bull is Perez.
Prez.
Yeah. Anyways, like this is not important, but
Mhm.
what I'm saying is if you're a purist engineer, this is where you and in
We
fact
don't have this in, like, more computer science
computer science is literally just this in hardware.
in hardware.
It's literally it's like this, but at like global level.
Yeah.
It's like Nvidia, and then there's like Intel and AMD, and they
Oh,
compete
that's
with
it.
each other to make the most efficient microprocessors. Funny you say that is like microprocessors also have a very complicated manufacturing process. I know
Mhm.
nothing about, but that's also
I know all
mechanical.
about it. Go ahead.
Do you?
No.
Yeah. But that's also something that mechanical engineers initially, and material scientists and mechanical engineers came up with that process. So the process of creating those, like, manufacturing a chip. Your hardware engineer in NVIDIA
Material
designs,
science, yes.
material and mechanical engineers. It's a manufacturing process.
Yes.
Yeah. So it was a mechanical engineers. In
And
fact,
a lot
I
of it
remember in
happens
undergrad.
in Taiwan, by the way.
Yeah, it happens in what's it called? Taiwan.
My new roommate is from Taiwan. He says, like, it's the #1 country in producing.
Yeah, it is the #1 country because TSMC is there. And it's like
TSMC.
they're like the biggest producer of chips for everybody, basically.
That's
Everybody. It's Samsung and them.
I think
that
it's
are-
top 10 valued companies in the world.
Yeah, because of every single GPU and stuff is being produced there. But anyways, like the race there is on a daily basis.
Mm.
They're trying different things, but your electrical engineer, hardware guy comes up with an architecture
Yes.
that they want to create.
Yes.
And then this has to be manufactured.
Yes.
And the manufacturing process is very complicated. You need clean rooms. You need it's printed onto a wafer. Very hard to do. Anyways, I don't know much about it.
Yes. Semiconductors.
Yeah, but that's where also there's like this race. So, like, how can we make the manufacturing process better? Or the purest engineering thing, right?
Mm-hmm.
F1 is
What
that.
about algorithms? I meant when I said computer science. Like,
Oh, so when you talk about software,
Mm.
also it's basically you see this on a daily basis. Like
Mm.
OpenAI competing with Google, competing with.
That's it.
Claude,
But he's
like-
not like, okay, let's come. Like, F1 is like, bitches, come here.
F1 is very purist in
Yeah.
that it's a sport.
It's a sport, like, so you get the best driver,
And-
get the best engineers, and I
you-
want
you
to beat
compete-
your company.
And you compete like very frequently.
Look, okay, Mercedes, we have like Mercedes, McLaren, they all produce cars for normal people
Yeah.
too, right? But they also have this thing, let's compete with each other on our best
Again,
version.
there's the old school days of F1 was not so good because these companies they didn't have much incentive to get
Uh-huh.
into this. These days they see this in like valuable for them in 2 ways. First of all, they make money.
Money.
They make money off of F1.
Because of
TV
the
rights,
TV rights,
people
and-
going like fans, etc. They make a shit ton of money,
Mm-hmm.
and they have sponsors too.
Also
Like,
get the brand for like
the
their-
brand recognition, sure.
They
but like
are,
an
they
F1
already-
fan already knows all these manufacturers. You're
Yeah.
not really. Yeah, the point is not brand recognition. I think for them, the majority of the point is for Red Bull, it's brand recognition.
Mhm.
Red Bull, they want extreme sports.
Yeah.
But for auto manufacturers, they get technology out of this, and they implement
Oh.
this technology in their actual like production calls.
Like-
Maybe not at the same level as F1.
Yeah.
But lessons learned can transfer.
Yes.
Right.
That's it.
Okay,
We don't have this for computer science.
we have this in software.
Where is the competition?
So, well, maybe it's not like this kind of competition
Mm-hmm.
where it's like very raw.
It's also very popular, right? A lot of
Yeah,
people.
there's
follow.
no like coding like thing or like okay.
Like
Actually,
it's not like
funny-
Amazon
yeah.
and Google and what is the other one?
funny video.
OpenAI.
Yeah, funny video I can show you.
Say
is-
okay, bitch. Let's.
There was this F1 autonomous race. It was in Dubai, and it was funny. It's like the funny videos that came out of this, where all these cars were just like really stupid. This is the software people doing their thing.
Oh, again, like
Yeah.
related to F1. Yeah, because competition is always interesting to watch. But like Google, yeah, they are in compete because they have.
I
Like,
have to do a lot of reading for my job.
Look at this.
Emails, contract.
Shut up.
why should like women seeking companionship?
That's because you're looking for dates, man. That's not. my
No,
problem.
no. This is my Chrome account, dude. This is my Chrome account that I only use for work.
Well, it's assuming.
It's just
It's still
assuming.
MIT. I think it's just MIT location thing. There's a lot. There's
They-
a lot of singles.
They
here,
just
guys.
assume that like if it is, yeah, this
I
is
wanna-
the best content that
I want to
attracts
see
people.
if this guy has the videos of them getting stuck somewhere. No. But it was really funny because I was watching the videos of, I was watching shorts. The cars, they go in there somewhere and they get stuck. They go, what the fuck am I doing here?
Mm.
Yeah. Anyways,
But
this
this is
could be
not
wrong.
the coolest. Like, okay, when you say mechanical engineering,
No. By the way, the
Cars.
people who coded these autonomous cars, they're mechanical engineers, the control people.
okay,
They could be CS people because CS people do robotics and control. As well.
yeah, of course.
Yeah, it's like that's kind of like the shared.
What would be the competition that we can have for?
I can't think of it honestly much. Because there's like IP protection. You want to make a product usually with software. You want to sell it to people.
Well, that will be their like cars. Like that will
Yeah,
be
so
like
that exists. So that's what I told you. Is you
that
got
will be
OpenAI, you got
the
Google,
general
and-
competition that these car companies have. Like if you want to make a comparison,
Yeah.
that they have and sell it to different people.
Yeah.
But if they want to have also very like a special event that they compete each other and
Like they can make their AIs and then the AIs can go against each other. Or
that's
something.
that's great.
But like Google DeepMind has their.
That's actually great. Like OpenAI, like a chess. I don't know, some game.
There's a chess. There was a thing. So Google made this AI for chess, and
Uh-huh.
then it trained with reinforcement learning. And you know Stockfish. You know Stockfish in chess.
No.
It's like the most famous chess engine.
Okay.
Yeah, it's very good.
Okay.
Like, it was like basically gold standard for
Mhm.
this thing, and that was able to beat.
Google.
No. That Stockfish was
Ah,
there.
Google beat
Google's
the Stockfish.
AI, like deep learning approach, beat the Stockfish engine, which is like a min-max. It's a modified min-max that goes and searches all the possibilities up to some depth.
Okay.
Because computational limit, whatever.
Mm.
You run Stockfish at its maximum capacity, as deep as possible, and you let that RL agent compete, and the RL agent turned out to win more than Stockfish over multiple
That's
tests.
amazing. Now we should have OpenAI and Google fight over a chess.
They could also do this, where both Google and OpenAI.
You know,
this claim of O1, for example, came out with OpenAI. Google had it a while back with their IMO model, which was a RL-based thing.
O1? Oh, the
Yeah, the
PhD
new-
student. Alright.
Not a PhD student, but yeah, the new model.
Alright.
But yeah, so they could compete at IMO.
Uh-huh.
Like they could just literally, when the IMO comes out, solve it, and we can see which
Don't
one
you
does
think
better.
they can solve it, all of them? Like the O1, how do you
O1 is the claim OpenAI has is 83% on IMO,
And
which is
I-
a shoe and gold medal, right?
Yeah.
But I don't think that that's necessarily true because the way they test these
This is
models is not
crazy.
very. Yeah, that is crazy. It's not very transparent though how they test these models.
Well,
they report 83%.
once Google releases their model, like
no, Google had it way back. I don't remember what they claimed, but it was 80-something%, like maybe 85%.
all right, now we can have another person outside of them that choose a test, and these two come and test.
Yeah, exactly. So that's called benchmarks that
Okay.
exists for LLMs. There's different benchmarks that LLMs do.
Yeah. Okay. I see
But
what.
benchmarks are not very good because you can exploit them. They're like kind of like set in stone.
Mm.
Like IMO, roughly what types of problems exist. So they are within a distribution, within a
Yeah.
somewhat known distribution.
Yeah.
So these models can't probably cope with it.
Like the thing about.
What I think, and this is something that's in my presentation too,
Okay. Right.
is that like out of distribution. How do these models do?
Mm.
Because pretty much everything we do with them is in distribution. right? They're becoming much more capable because the distribution they're capturing is becoming bigger and bigger, and they're able to capture it properly, right? Like you add math and like reasoning to it, it's trained on something, right? And that something has a distribution, right? But what happens if you go outside of that? You know, a artificial general intelligence should not be distribution dependent. Like it shouldn't be like, oh, if I give you a surprising thing, you can't cope with it. Like if you have actual reasoning capabilities, okay, you know.
It should extrapolate.
Yeah, so exactly. Like when Einstein was thinking about relativity, that's like completely undefined. It's like Newtonian physics is all everybody
That's
knows.
actually always true. We want to have a model that helps us once we are not in a situation that we are not used to it.
Exactly, but Newtonian physics is what we knew, and Einstein
Yeah.
was like, okay, let me go somewhere weird. Right. You know, light, the speed of light is perceived the same for all observers.
I see.
It's kind of meaningless in Newtonian physics.
All right. Yeah. Okay. This is.
Now, I want that for these generative models. What's that out of distribution thing? Like, you know, you say O1 has a PhD level intuition.
The thing with O1 is that okay, they can compete against each other over an O1 or even over chess.
Yeah.
The thing with, if I wanna make the comparison again, F1 is something simple. Like if you wanna make like audience or have like fans for one, like F1. Okay, I'm seeing this car is driving much faster than the other one.
Yeah.
Right? And then there are like, I don't know, cheerleaders popping champagne with the drivers. These are makes it exciting for the people to
That's
watch.
the entertainment value.
That's the entertainment value. I said this competition should be entertaining as well.
Sure. I mean,
Right.
you can add.
I want to make a competition that is entertaining. I was thinking chess.
But this is not a bad idea.
Chess may be a good one, but even
Chess is kind of like a solve.
boring. It's a solved problem.
More. I mean, it's not a okay. Infinite compute, then it's a solved problem. But no, what I'm saying as a solved problem is that they are kind of competing at such a high level.
That normal
it's
people
imperceivable. Even the grandmaster looks at the move and it's like, okay, that doesn't make sense to me.
not
And then
intuitive.
it turns out that that's like the best possible move you can make. It's not super like relatable.
Yeah,
As
not
human
relatable. Yeah, we want some competition that is relatable for human beings.
Yeah.
And these motherfuckers compete against each other. Like F1 is relatable to us.
Yeah, I mean, cars going fast.
Cars going fast.
Yeah,
and
that's,
every day we drive. Also, we can also drive every day. So
Yeah. Well, I mean, okay, like, you know, team sports and stuff, people can play on their own, you know.
Yeah.
I don't know if AI is something people can do on a daily basis.
Well,
but
they
something-
tried to fight Mark Zuckerberg with who was the guy?
Elon Musk.
Elon Musk. That was a good first step try, but we need to have it stronger. Camera is there. Right? That's a good thing to have. We can make a lot of money out of it. Dana White.
I don't know what that could be. I mean, the robotics games are kind of
So
fun.
that's that, but okay.
But robotics games are like, again, it's a mechanical thing. Like, you know, the fight robots, have you seen those competitions? They're
that's
really fun.
mechanical.
And they get sponsors, there's money in it. But that's very mechanical.
That's very.
I feel like everything we can have fun with is the physical.
Physical.
Like, we need the physical thing.
Yeah, we need the physical thing
Yeah.
exactly.
So, or it has to be like a game that is very entertaining to watch as it happens.
Yes, a game that is entertaining to watch.
Like
too.
esports is the thing these days. Like people like, it's bigger than some of the conventional sports.
That's actually great.
Like FIFA.
What if they make FIFA or like Counter Strike that OpenAI is fighting Google?
That's doable.
That's also very relatable because we can play it.
Yeah. That you can do that probably. You can have like AI players.
Yes. Well, they have
For
it
games.
already. Counter itself has it.
Yeah, but it's not good.
Yeah, it's not good, but we can do that, and it can be very relatable.
Yeah, and you can also pit humans against AI too.
Yeah. Well, I think they destroy humans, right?
Probably.
Yeah.
Because they have like very precise inputs,
Yes.
which humans can't have.
Oh shit! Yeah, they have everything.
Yeah, they have like full control of. So that's maybe something we can also add to the challenge is that they don't have raw control. They basically have to move a mouse or something.
Well, that would be mechanical again. You know why? I like to remove the mechanical part.
Yeah, usually like pure software.
So that it is more on focus on software. So, but one thing I like the word was relatable. It should be relatable for other people to watch. It should be entertaining, relatable, and these big companies against each other.
Yeah, entertaining, relatable,
Like
and
they
a lot of
have
money, basically resources.
Yes.
Yeah, so you get the best people on the job.
Yes.
Yeah, I feel like if I was a software engineer or a researcher, and
Bro,
like the
that's
pay
the
was
thing.
similar
Mm.
for something like that, F1 for software versus normal software job, I would definitely.
I would definitely.
My preference would be to do raw.
It
very
is like
raw
full of
competition.
trash. Like Amazon, I will fuck your ass.
Yeah, you get like the Amazon team shitting on the Microsoft.
That would be
team.
amazing.
Yeah, I don't see that in most software engineers. Like tech bros are not like that, but.
Well, I think once we put it, they grew
Yeah, yeah.
towards that.
Yeah, I think that will come.
That
Like
will come.
esports, there's some of it. It's a
Yeah.
little nerdy, but it's still there.
Yeah, engineers in F1.
Yeah, engineers in F1, they're also like kind of nerdy, but
Trash
they-
talk
they-
against each other.
Yeah, like, I mean, not you don't see it, but in
I
the
see.
background, I'm sure like people are just shitting on each other. Like, ah, that guy's a dumbass.
Well, we know that scientists do that on Twitter all the time.
I do
right?
it. I do it at MIT. Like, I go to somebody's talk and I'm like, that was trash, man. I was like, this guy doesn't know what the fuck he's doing.
Okay.
You know, like this is like all researchers do this.
Yes.
Yeah. No.
Like, because everybody has ego.
There's some ego, but also there's some level of it, even if it's not my field of research, but if I understand it, I'm like, yeah, that shit is not going anywhere.
I
You know?
see. Even if you're very honest.
Yeah, even if I'm just being honest,
I see.
I critique myself that way too.
Mm.
Like I look at my work and I critique myself very harshly. I don't have a high opinion.
That's
of my
an
work.
engineer. That's an engineer. You should
I
not.
don't-
You should not be in your life like that.
Yeah, I don't necessarily have a high opinion of my research.
Uh-huh.
I've grown to accept that what we do in academia is not always the most exciting thing.
And once in a while,
Yeah, once in a while
happens.
this happens. But generally, I've grown to accept that what we do in academia is not necessarily going to be
That's true.
exciting or whatever. But so basically, I've come to terms with accepting that what I do does matter, but maybe it's not as impactful as I thought it would have been.
Mhm.
Like when I was coming to MIT, my thought was, okay, we'll do like groundbreaking research here.
yeah.
Right, but that's just not true. Like nobody is doing that kind of, and the people who end up doing that are mostly lucky.
It's like the
mo-
exception, right?
yeah. Like most of them just get lucky. They find something like that was like very weird, and they just get lucky basically. Like the majority of the cases, it's not a very calculated.
Yeah,
thing.
you cannot plan to do an
To change the
amazing
world.
work,
Yeah,
right?
exactly. You can't plan
You
to
can
change the
do
world.
your work in the best way you can, and
And then maybe-
hopefully,
or at your own level, whatever impact you will have.
yeah.
Yeah. So that's something they have come to terms with. I think something like F1 makes it exciting, even though
Makes it
what they
exciting.
do in F1 at the current level, like the optimization of every single little thing, it's not practical for the real world anyways. Like most of that effort goes
Yeah.
into just winning a race.
Yes.
Yeah, but it's still fun to do.
It's
You
fun
know?
to
Like, so
do.
you can enjoy the work without, bruising your own ego about what I'm doing is not changing the world, right?
That's true.
Right. So that's just coming to
I
terms
mean,
with
world
that.
is already at a good place. To be honest, doesn't need to be changed much.
I mean, there's always room for improvements, right?
Yes,
So, yeah, I think that's a good thing to.
they can put their own head on it too.
I think most
if
people.
it is countered, they
Yeah.
can put their head on.
Yeah, so they can play games against each other or
Yes.
whatever it is. But pure software competition, I think it's a great idea.
It's a great idea. Competition is always entertaining.
Yeah, I just don't have anything in my mind right now that
I think
can
that was a great idea.
tangibly tell you what to do.
We made it. We made it happen. We need to send this
Maybe,
idea.
maybe you should make a startup.
Yeah.
Like when Dana White did the UFC stuff, when he bought UFC.
I will be the.
And it was worth nothing, right? It
Yeah.
was a failed company, and he made it into something that was
Yeah.
entertaining. Maybe you should do that. Maybe you should make a company about like getting software competition going.
Dude,
Like,
actually, it can
entertaining.
be just bunch of engineers who wants to fuck
All
each
you
other.
need to do is define your rules and
Yeah.
get a bunch of sponsors to have like a tangible prize, like a good amount of money.
But we need to
as
work
prize.
with like a good gaming company so that
Yeah, good gaming company, whatever it is.
that it is
whatever
beautiful to
collaboration-
watch.
Yeah,
It's beautiful to watch.
Whatever collaborations that you can do.
That will be like a movie. Why don't we have it already? It will be like a movie of war.
I think there's a couple of reasons we don't have it already. Is that first of all, the interest in that kind of competition, it's kind of an unknown, right? Like UFC initially had no fans.
Yeah,
Right,
but
like-
fighting is always interesting.
Sure. I mean, you can say that, but UFC existed for a while without any fans.
Mm-hmm.
Right. But if you market it properly, then it can become
Yeah.
something bigger. So you got to
That's
market
a
this
great idea.
properly, and then there's also the issue of the highest level talent in software engineering, and so on. The best researchers in this space.
Like UFC is all the best fight.
Yeah, it's the best fighters in the world. They wouldn't want to do this
League.
because
We should have a league. That would
yeah,
be.
they wouldn't want to do this because they're now working on whatever it is they're working on that they deem to be like the ultimate level of like the purest thing they can do, right?
Okay.
To get them to do this requires some form of, you know, you need to get somebody who's really good and famous in that world to commit to doing this, like to submit a team basically.
Yeah, that's true.
You
We
get a
need-
bunch of
we
those
need
people in, and then other ones will. This is the thing.
a gaming platform.
You know,
some good-
everybody thinks that like software engineers are they're nerds. They don't have like they have fucking massive egos.
Yes.
They will start shitting on each other, fighting for winning all
Dude,
the
this
time.
is amazing, and they fight already with each other
Exactly.
probably. Just we want to make money out of it by showing this fun experiment to other
Yeah,
people.
exactly. So they try to get them to make the weird, and they can put the rules on it. Like
Yeah.
the AI model has to be like, for example, you say it has to be a machine learning model. There's no heuristics allowed.
Yes.
Right. Like no heuristics allowed. It could be like
No shooting in the dick for
the
sure.
size of the model has to be X. The rate at which it
Yeah, you-
produces inputs for the
Like-
game has to be more than this, less than this. Like F1.
Capacity on your computational model. I don't know power.
Like, so like F1 has that, right? You have a power limit.
We can have way
You
different
have a
weight
horsepower
classes.
limit. You have an engine size
Oh,
limit.
really?
Yeah,
Right.
yeah, all of these exist in
Yes.
F1, right? The weight limit, all of this, so you can apply the same.
Yes, we can have different weight classes. For example, say okay for like different computational power classes.
Yeah. So
That
then,
would be amazing.
then you'll start to see maybe some very
Dude, and
insane
you know-
creativity.
Instant creativity.
And that could become applicable to like their actual products later.
yeah.
Like you know the tiny ML and like making
And then we can have the video, like there are like 5 people against 5 people shooting
Yeah,
each
yeah,
other, and then we can video, like we can have a camera, not the camera, but okay, what is
you can make it into a spectacle if you want.
yes,
Yeah.
that would be great, and we see how they fight against each other.
I mean, honestly, it's not a bad idea. Yeah.
It's amazing idea,
It's not
bro.
bad.
That was amazing.
Yeah. It's not a bad idea. I mean, I don't know. You gotta explore.
How can we do it, dude? Let's apply to Sandbox.
You can actually. This is not a bad sandbox pitch. Yeah, honestly, I mean they won't give you much money, but
Okay.
I think if you make your
Dude, this is the Sandbox pitch. What are you
yeah,
talking?
this is a good sandbox pitch, but you need to be more concrete about exactly how you want to go about it.
That's you. That's on you.
Yeah.
The difficult part's on you.
Yeah, we can actually. It's
Actually,
kind of
let's-
a fun thing.
That's
I like
super
doing
fun.
things. Yeah.
This is super fun. I love the word relatable. That solved our puzzle.
Yeah. This is actually a fun idea.
Like chess is bullshit. We cannot see what's going on chess. It's too much difficult.
even chess when humans are playing is boring to watch.
Yes.
For hours, they're just like.
Like,
okay,
if
let
you're
me-
not a
Let me look at
professional.
Magnus Carlsen writing some shit on his paper. Like, okay, no.
And like they are thinking 10 levels ahead. Okay, we don't understand that.
No, it has to be very human.
Yeah. It should be something you can do.
No, you can relate. Like,
Yeah, you can relate.
yeah, that's the
Exactly.
thing you need. So F1, you can't do it. But
Yeah.
if somebody gave me an F1 car, I would crash immediately.
But they are against each other. That's so cool.
Yeah.
And we can have like even UFC is like the best league. We have it created this culture that we have minor leagues that people against each other are against each other. So we can have engineering teams against. And actually, it will be very good, like team creation. What is it? Team bonding, whatever for engineers inside each other's company. They're like, yeah, let's go beat the other team.
Yeah. It's a good bonding experience too. Yeah, I mean, it's worth looking into it.
I think a lot of the structure is already set. For example, if they want to play counter against each other.
Yeah, I mean those are possible ways to do it. You have to be also like you have to like do some basic tests to make sure that it is actually challenging. Like because if there's a game that you can become perfect at with very little effort, then you just kind of cap everybody becomes the same, and
But
then it just becomes a little bit of like a randomness.
So how do you say?
Because all games have randomness, right? Like
Yes.
It's built into the game.
Yes.
And then it becomes like, okay, if you run this thing enough times, everybody's like equal.
But
You don't
the
want
thing-
that. You want it to
The
be
thing
actually
is that the competition against each other creates randomness, right? They
yeah,
got-
yeah, yeah. But what I'm saying, the platform on which they compete has to be, you know, I don't think fair is the
Like
right word.
we give them the DDoS too.
Yeah, I don't think the word is fair, but something that is, I don't know, it has to be, there has to be some merit-based outcome. Like if you have a better model, you should always win. Like whatever platform
Well,
you test on.
winner is the person who wins. Yeah, I say the game should not be like fitted
The
in a way.
randomness should not be so high that all like there's like a few strategies and then every AI model or every code becomes the same. You know
That's
what I mean?
true. That game
Because
could
then it
become
becomes very
boring.
boring. Because
Yeah.
everybody's just doing the thing, and then who gets lucky gets to win. That's not great.
Yes.
You don't want that. You want something that is less of that and more. Yeah, and you want the game to be hard enough
Mm-hmm.
that AI can't just do it, and then you also don't want the game to be so human and so hard for AI to do that the AI is just doing nothing. It's
Dumb.
boring.
They're dumb,
Yeah.
right?
So it's hard, but you know you can.
Wait.
You can
Look,
think about it.
look at Counter, for example. Do you think
Yeah.
it doesn't have the element of randomness?
No, it does, but it's okay to have some randomness.
Yeah.
What I'm saying is that so statistically, like the expectation shouldn't be changed based on the noise. Like that noise should be robust. Like your performance should be robust to the noise. Like whatever platform you have, that noise should not alter the outcome significantly.
Yeah.
So it can't be completely stochastic. You know what I mean?
Yeah.
Like
For example, in UFC, what is the stochastic, or what in F1, what is?
Well, in F1, the stochastic is you can have an accident, tire blows.
But it comes from the interaction between the players.
Yeah, but that's fine because you get so many races.
You're not saying the field should add some randomness
yeah,
by
yeah.
itself.
Yeah, but like
Maybe you say
you know, you
win.
do everything perfectly, but sometimes things go wrong.
Yeah.
Your car breaks down. But that's fine because you have so many races that over the whole season you see Red Bull winning 7 times and the next team only wins twice.
I see.
Yeah. It's the same thing here. Like in UFC, you can get lucky. You get a lucky punch in and you knock somebody out.
What if, for example, an engineer write a line wrong and the code is
Yeah,
terrible?
exactly.
Right?
Yeah, that's fine because they get another chance later.
Yeah.
Like it's a league basically.
It's a league.
Yeah, so like it's the same thing with in UFC. It's like you can get a lucky punch in,
Mm.
you maybe knock somebody out, but you're not gonna be champion
Mm.
doing that. You need to win many fights. You don't need
One
you don't
other
win one
thing
fight.
Is that human beings are live in F1 and UFC, both of them,
Yeah.
are live controlling the process.
Yeah.
Here,
There could be some level of like adjustment allowed.
right?
Yeah, where like the humans can just make it change, like every round.
Every round.
In like Counter Strike, they're like, okay,
Because-
this thing they can like crank up one thing and the other, and you know try to like adjust their model or something.
Yes,
between
because
rounds.
fight is between the two people. It's not fight between coaches,
Yeah.
right? If engineers are melding a model, another model, and they are once the game.
Well, it's like team sports. There's multiple
Yeah.
people involved.
Yes.
Yeah, it doesn't have to be an individual sport.
Yeah, team sport for sure. I like it like be 5 people.
I think F1, it seems like an individual sport, but it's a team sport.
Yes,
Yeah, it's not an individual sport.
that's true. But there is always a human being. Like even if you play soccer, the attention is usually mostly on the forward player,
Yeah.
striker. So here we need still some.
Chief engineer.
Yeah, something that is like the leader, something that does the last touch.
Yeah, you need to add the human level,
FX.
something human to it.
Yes.
Yeah, it's interesting.
Okay, we should do it. We should do something about it.
I'm willing to give it a go. Yeah.
Right? That's a good idea. Okay, we don't put it on YouTube because the idea will. No, we will put it.
It's fine.
We will put it.
Yeah. It's a.
Oh shit! Sorry. I mean, I have to reply an email.
Sure.
Let
You can cut
me
this- you can
pause
cut
this. No, we can pause it and come back in a second. I forgot.
Sure.
So, yeah, the game should be constant,
The
right?
game has to be a set in stone thing.
Like
At least for every game.
4 or 5 sets in a round. So
Yeah.
that-
So a few rounds they go and then that's it. And then, but like if you update the game for the next, the game can change basically slightly or whatever. For the next set of competitions, then you release the game beforehand. The teams will get X amount of time to do their AI thing, and then they can come and compete.
How long is this X amount of time?
Okay, these are variables that you have to set for the race.
So you
or for
cannot
the
tell an
competition.
engineering thing you have 1 minute to.
No, 1 minute is not reasonable. It has to be reasonable, of course.
Yeah.
But like any competition comes with its very specific rules and limits.
Mm-hmm.
This is the same.
Yeah.
You have to have some rules, otherwise it becomes meaningless.
Yeah. Every year we can have a set of rules.
Yeah, F1 changes the rules every
Yeah.
now and then, yeah.
All right, let's do something about it. All right, let's go now. Jump to your. We just got distracted a lot.
Yes. So my research, applying AI and machine learning to mechanical engineering tasks, where where we think it can be useful. And we were talking about mechanical engineering, what it is, and what kinds of things. But yeah, we've gone over manufacturing, basically anything that moves, more or less. It also involves like HVAC, things like this is also mechanical engineering.
Oh, the AC.
Yeah, like power generation.
What is your thing?
So my thing is design. Like it's very pure. It's like just like the concept is design.
Design whatever.
Well, design is a discipline. Design is not whatever. There's different kinds of research in design. There's like research about how people interact with each other, like teams. How you can do that stuff, or it could be specific design tasks. So optimization, for example, is one of the disciplines of design. Like my advisor's background is in optimization.
What is the definition of design?
Oh, it's a very complicated thing. Again, like it's a multidisciplinary thing. It's there's art.
Yeah.
There is
You are an
engineering.
artist now.
No.
You're
So
not an artist.
No. We don't work on but aesthetics, things like that. Design is a very abstract concept. There's
Yeah, it's
textbooks-
very abstract. It
Okay,
can be
there's
very
textbooks
general.
about like engineering design,
Okay.
and that's sort of where the mechanical engineering part is engineering design. It's not purely just design because the design involves, art and things.
A
like
whole
that.
product.
So, for example, in CSAIL, there's labs that do design work, computational design. Right. This involves like Illustrator or like Photoshop or things like these are
okay,
software.
okay.
These are design software.
Okay.
So those people work on algorithms for that kind of thing.
Mm-hmm.
Right, and make those softwares.
Mhm,
Do
mhm.
research on like what are the things that people use and how we can improve them and so on. Engineering design in the mechanical sense involves optimizing performance. It's like optimization is one of the things. That's what my background, my PI's background. What we do often involves some sort of optimization. At a very abstract level, optimization basically is inverse design. It's usually in textbooks that's referred to inverse design.
Optimization is inverse design. You wanna
So you have some performance requirements, some constraints, whatever,
that's nice.
right?
Yes.
And you want to get to your design. Like it's like a direct design thing.
Yes.
It's like, I just give you what I want, and I
Wow.
define the world that I want this to happen in, and then you give me the design. Right, it's computationally or otherwise. I don't care. Like if there's a
But
closed
we are
function.
saying once an artist probably is designing, they may not have a goal at
So yeah, their objectives may be very
vague.
abstract.
Yeah.
It's not a mathematical objective, right?
Yes.
So I want it to be beautiful, or I want it to be pleasing to the eye. What is that?
What is that?
It's
right?
subjective, first of all. Like,
Very
depending on
subjective.
culture, person, it changes.
Mm-hmm.
So there's like that artistic aspect to it. There's the creativity and so on. So I have some papers on like creativity in design.
Mm-hmm.
We explore creativity in AI.
Okay.
That's a very old research that I did.
So what is it?
So textbook, or like if you look at papers.
What does creativity
Exactly.
in artificial intelligence mean?
Yeah. So
I'm just trying.
not artificial intelligence, but in design. Like, forget about artificial intelligence. Just in design, in engineering design, what is creativity?
Okay.
Okay. There is many different definitions. Like different people have had different definitions.
That will be like being an artist in an engineering field.
Not necessarily.
If we say artist is a person who just expresses themselves and then it turns out to be something beautiful.
Yeah, exactly. So that is kind of the most high level way to describe creativity in engineering design.
Okay.
For example, when
Who is an
for example, when
who is a designer like that?
like Benz,
Benz?
yeah, when he came up with the internal combustion engine, right? Like nobody was doing internal combustion.
Ben, who's Ben?
Like Mercedes-Benz is.
Oh, Benz. Oh, it's the
Benz.
name of a guy?
Yeah.
Alright.
He named the company after his daughter, but yeah.
Okay.
Anyways, like when they came up with, it was the first internal combustion engine.
Mm-hmm.
Nobody thought of a thermodynamic cycle, because the steam engine was the only thing people knew at the time.
Uh-huh.
Like internal combustion wasn't a thing.
Mm-hmm.
But he was like, you know what? Instead of burn the fuel, create steam, run it through a turbine,
Mm-hmm.
and get power out of that, because it's not very good for cars, right? You need immediate power, and you need to adjust it very quickly. We'll just pump fuel and air
Actually, that's
in the same place,
so right.
and then like spark it or high pressure ignition, and the ignition will run.
Actually, you know
But
what?
that's creative because it's not.
This is creative.
This is not
and
anywhere.
From my point of view, this doesn't have any objective function. He says, I want to establish something completely new.
Yeah.
He didn't make the best combustion engine. He just made a
You
combustion.
made a combustion and the internal
That's
combustion.
the
engine.
problem with, like, okay, not the problem, but the differentiation is optimization is
It's
inverse.
a known.
Yes, you want to just improve something.
Yes.
But the creative design, you want to really create something. So
Yeah.
if we have inverse design, which is optimization, and we have creative design, I think the names are very nice here.
Yeah. So creative, usually people define it as the consensus kind of way is
Is you will be an
novelty.
inventor.
Yeah, novelty plus value / performance.
Yeah.
So the novelty is
Like
nobody's done-
Alexander Graham Bell is a
Yeah, yeah.
very creative
Yeah,
person.
that's a creative design because nobody's done it before, so it's novel.
Yes.
That's criteria one is novel.
Dude, that's what engineers should do. Actually, I hate optimization.
Well, optimization comes after.
Comes after.
Yeah, optimization comes once you have a defined problem.
Yeah. And
That's
now,
so
like the
required.
optimization. Oh, it is important for
Yeah,
sure.
It's something that you need. Yeah.
Yeah, of course. But I think that part is like you're God and you created something.
Yeah.
This part is like, okay, I improved. Like, yeah, who made lamps today so good, but compared to Thomas Edison?
Well, the people who came up with LEDs, that's creative.
That's creative, yeah.
Right. But yeah, this is the thing. It's like optimization is like in a well-defined structure, it can work.
Yeah.
You go outside of a well-defined structure, then there's no such thing as optimization because you don't know your objective, you don't know your
Yes.
constraints, you don't know your design space.
You're
What is your
lost.
design
You're
space?
lost, and you have to come up with
Yeah,
something.
so creativity is a weird concept. And even in known fields, like if you're designing cars,
Mm-hmm.
what is a creative car? Like
What
is
is it?
Cybertruck a creative car?
Is it? I think
It's creative in ways. In some ways, it's creative.
yeah. It's
right?
a nice try.
It is novel.
Yeah.
It is definitely novel, but like performance-wise, will it live on? Like, will it become a new era? Is it a new design?
Well, electric cars for sure.
Exactly. So like
Electric
making it-
car is creative.
Electric car, the concept may not. It may have been floated for a while.
Yeah.
So yeah, but it is different, right? It's
Yeah.
not internal combustion.
Well, okay, what is the difference? Like, okay, we had Tesla electric cars and suddenly Cybertruck. What did it add? I don't.
Yeah. So Cybertruck is exactly. And I think it's just more of the
Wow.
aesthetic design of it.
Yeah, it is just a design of a car which is also a bit bigger than other electric cars.
Well, yeah. I mean,
I
there
don't-
is
I don't-
already no. There's electric trucks other than the Cybertruck.
Alright, I don't see what is novel in it other than, okay,
Aesthetics is novel.
that is not
The way it
novel.
looks.
This is not
No.
impressive. That's what I'm saying.
Yeah.
It's
I
not
mean,
impressive.
not every creative thing is, again, there's two things. There's novel plus performance. These are the things. Engineering design, I think, that those are the two criteria
Yes.
for creativity that most people agree upon.
Mhm.
The novel, Cybertruck design, or like the looks of it is novel, but is it actually useful.
Mm.
I don't know.
I don't think so.
Yeah, exactly. So that's where creativity in engineering design is. But anyways,
I think creativity is like, yeah, you can say if something is creative and in design,
Mhm.
if it opens new venues for optimization that
Exactly, like
that
if you-
haven't been before.
yeah, it doesn't exist before.
Like brings your performance level to another, like optimization is like we have 80% work, let's make it 100%.
Yeah.
Now you add something, okay, we are working 20 times better, like machine learning. Machine learning is creative, like GPUs.
Yeah,
right?
so when AlexNet came out
Mhm.
in 2012, which was the first sort of the second boom of machine learning,
Mhm.
it was creative because nobody thought to build a model like that.
Mhm.
It was like two things. Was it purely statistical, so it was completely data driven, and it had no component that was heuristics. Like there was no
Mhm.
human component.
Mhm.
It was just a bunch of parameters, and you optimize those parameters to perform classification.
Wait a second, what was before machine learning that was human based?
People had heuristic algorithms for classifying images.
Okay, okay.
They would do like canny edge detection and try to
Mm.
grab features that were common in one class, and
Mhm.
you know, like it was purely heuristics. Like nobody was doing learning
I see.
in that sense. I mean, learning is just optimization, but whatever.
Yeah.
Yeah, no, that's kind of where it is. Anyways, my work mostly is on optimization and inverse design.
Mhm.
My work does.
Most
Again,
of the students are.
I mean,
like-
yes, it's a better defined problem. Anyways, I did again some
Like for
creativity-
example, me too, right? I'm doing these works. I right away. First thing I do is okay, come up with a model. Okay, for me, I think creativity is coming up with a model. It is optimization. Okay, what is your objective?
Yeah.
In this model, find the objective function. Like find the best that maximizes the objective.
Yeah, I mean, yeah. So like in your data markets research,
Yeah.
it's like, okay, how do I guess I don't know what objectives you look for.
Maximize
Like
welfare.
maximize welfare, whatever it is,
Yeah.
and you define those objectives and constraints, and you just
Mm.
run your optimization or solve your optimization
Yes.
problem. It's a linear program, nonlinear, whatever it is.
Yes, yes, yes.
Yeah.
So okay, is it for you, is it the same that you have a first step that you create a model and then try to optimize it?
Usually it's like so a lot of times it's a established problem at least, even if
Oh.
it's not formulated as optimization. And then we try to build a machine learning model that can perform that task better than if you were to do optimization, or better than a human designer.
Okay.
Right. And
So give me a second, I want to compare.
value proposition a lot of times is time savings, so it's
Mm.
quicker than optimization and or humans. Performance is sometimes that's the case. Sometimes it's a unsolvable problem, like it's or not unsolvable. It's a very difficult problem to solve, and then you demonstrate that using AI you can solve it in practical time, and better than optimization. Wait, sometimes if you have a bi-level optimization problem, okay, that's one of the researches I do is on linkage mechanisms. Like,
Is it
kinematics
this one?
and this? No, this one is a very simple one. This is like a conference paper.
Okay.
In that case, you have bi-levels. You have the low level is combinatorial. So you can't. The traditional optimization is kind of hard to do for that.
Okay.
It's NP hard.
Mm-hmm.
The feasible space is massive.
What
For
is
the
the
low level.
problem exactly? Why?
So kinematic synthesis. Okay, the demo may be live. Yeah, so maybe the demo's not live. I'm gonna check out my phone if it's running.
Oh, okay, it's your thing. All right.
It should be. It should be there. Maybe I typed it incorrectly. Design dash AI. That MIT. Do you have internet here?
I do have. I checked it.
Huh. Well,
Let me check on my phone.
the demo is live, so I can see this.
What is it?
Design-ai.mit.edu. It just says can't be reached. Yeah.
It is here.
Yeah.
How don't I have it here? Oh, wait a second. I may be able to. How is that possible?
Maybe your connection is connected to like
Connected. We have internet. We can.
maybe you typed it incorrectly.
Dude, I looked at this and put it here.
I know, but I'm just making sure.
Design.
AI dash AI.
Where is dash? No, this one is just on the phone. That's possible.
That's weird. Because it should be. I mean, maybe. Okay, maybe try design AI slash linkage. That's where.
Is it something designed for?
It's a
iPhone?
live demo, but I can. That's like I can show you what that problem is.
Mm-hmm.
The basic idea is you want to create a mechanism.
Can we throw your phone on the desktop?
I don't know.
If it was this, I could do that.
How do you do it?
I
Mirror
have
it?
this like Samsung Smart View.
Oh yeah, so this I don't think we can. I can like, try to mirror onto
Yeah.
something,
Yeah,
but I
try
don't think
to.
that's.
Not on
this
the
works
HP.
here. I don't know if you can mirror onto Windows.
If it's here, it should be here, right? Screen mirroring,
Yeah.
connect, project, alright?
No, that's
No.
for like yeah.
What is this one? Connect. Display on audio device.
Yeah, I don't think that will pick up the phone, but
No? Give it a go.
I'm trying to find it. It doesn't show up here. Yeah, anyways,
Alright.
it doesn't matter. I mean, I can show you something else to
Alright.
to you
Yeah.
to understand this. So our lab website comes up
Okay. Where are you?
here.
Okay. Dude, look at your hair. How much you changed, man.
Yeah, because of the long hair.
Yeah. Alright, good.
Let's see if project page is up.
Oh, this one was the attention all you need thing.
What? No.
It was about attention, right? You talked about it.
There's something in the paper, but yeah. Yeah, so the basic idea is you have these mechanisms, right,
Yeah.
that generate some curve, some path.
Mm-hmm.
And let's say I want this target curve, or like this curve.
Oh, do you
Like-
give a curve?
Yeah. So this is what I want to trace, and I have only one motor. I
Wait,
want like full
check
actuation.
if we are showing it to people. Yeah, okay.
Yeah, I have this like target curve,
Uh-huh.
and I'm trying to come up with a mechanism that traces this.
Alright, yes.
So feasible space is, any mechanism that has 1 degree of freedom, and doesn't lock.
This is, what is it? This is constant, this is moving.
Yeah, those
This
are,
is-
and this is the motor. So this just rotates.
Oh, these are motors.
No, these are ground, and the yellow line
Uh-huh.
is the motor. So this thing just rotates.
Okay.
Like
this
it's a full
rotates.
rotation,
Alright.
and everything else is just a constraint on that. So you can like add a node here, and then connect it to.
Oh, we have
these.
only one motor.
Yeah, there's no control system here.
Okay.
That's why it's like a hard problem. Otherwise, if you have 2 motors, then to come up with a control system.
Yeah? I don't know. Okay.
Like 2 degree of freedom, 2D. It's
Yes,
2 dimensions,
yes,
like you have
yes.
2 motions.
Ah, okay, okay.
Right, and this thing just traces that. Right, that's not.
So
The
you
comparing-
are here, okay, more than 1 degree of freedom because you have these extra nodes that you can have, but it's not 2 degree of freedom that.
It's a 1 degree of freedom system in 2D. You're trying to build a V mechanism.
Yes.
And this is just, you can think of
Wait
this
a
as
second.
a graph.
What if it was 2D thing? How would you do that? For example, this curve.
This curve, if
Yeah.
you had 2D, is a robotic arm. 1 actuation here, 1 actuation here.
Oh yes.
You
That's
just
move the base and then move.
Look, figure out what the relative motion of the 2 motors
Yes.
should be.
Okay.
That's, you can solve that problem.
So motor is not just going in a circular way. It can
Yeah.
be linear.
So in this case, we only have the only actuation we have is one rotation.
One rotation.
That's it. That's
Not even going over it probably periodic, right? It goes over itself.
Yeah, but the point is it's a closed curve here.
Yeah, okay.
Right? Like you want to just trace this.
I see. Okay.
So the space of feasible solutions is all
Oh,
possible.
that's the topology project you worked on?
No, that's a different one, but this is the graph topology. It's a graph. Like
It's a graph, right?
Yeah, this can be a topology.
You say this is a circle, this is a grid. From a topological point of view, they are similar,
Yeah.
so we should be able to do it.
Yeah, so if you try to do this
Uh-huh.
with optimization, your feasible space.
What is the optimization here?
Optimization, this is your target, and your
Uh-huh.
constraints are, this thing shouldn't lock. Like this mechanism can lock.
What do you mean lock?
Okay, so if I moved this joint here,
Uh-huh.
now if this wants to, or like,
Hit the ground.
no, if this thing wants to do a full rotation,
The
this
other
link
one.
is not long enough. So we get stuck, like you
Do it.
see?
Yeah, it hits the ground.
Yeah, it got stuck here.
I see, it hits the ground.
But it
when
doesn't
I
hit
say-
the ground. No,
here,
no, no.
here, look at this.
No, that's not what the problem is. Okay,
So what-
you see, this is fine. Like this is fine.
Why didn't it go all the way?
Well, that's because you solve the motion.
Oh, okay.
It's constrained. See, that's where it locks. So because this thing wants to go in this way,
Uh-huh.
this is not long enough.
So it hits the ground.
There's no ground. There's no line of ground.
Wait, what is
Okay,
the
fine. Let me show you the.
No.
let me show you something else.
What is stopping it here?
Hmm?
What is stopping
Okay,
it?
the length of this linkage
Uh-huh.
is, let's say, like 1 meter.
Okay.
The length of this linkage is 2 meters, and the length of this linkage that connects them is like 5 meters. This goes here.
Oh, okay,
It
okay.
can't- it's
We
not long
don't
enough.
have. Oh, yeah, I got it. All right.
So
Can
constraint
we have
is-
it in a slow motion so I get?
I don't think it goes in slow motion, but like it shows you the parts of the motion that can happen.
Yeah,
It's
go
here and
go.
here.
All right. If it is here, for example.
That's where it gets stuck, and then the rest of the motion can happen here. But anything
Okay, I
in between
didn't
them,
get why exactly. I understand why it can't, but in this specific case, I want to know why exactly it can't get there.
yeah, it's a very simple.
Like, okay, we are here. Let me share also with people. All right, draw it for us with your two robotic arm.
Oh, well, robotic arm is very simple.
No, I'm joking. Why? Show us why it gets locked here. Yeah, I think I got the big
The
intuition.
very simple thing is if you have this grounded here,
Yes.
and this thing is here,
Mhm.
right? And then this goes here, and then you have another ground here, and this is the link, right?
Yes.
Let's call
okay.
this state 1,
That's the state one.
and then this thing is going to rotate in this direction.
Yes. Go ahead.
In state 2, what you're going to have is your ground joint,
Mm-hmm.
the two ground joints. This thing's going to be here,
Yeah.
this is going to go there, and this thing's stretched out all the way. Right. Any further motion of this is going to push it this way.
Yeah, but
This
this
is not long
doesn't
enough.
have long enough. I
Yes, so
see.
it can't go in this direction.
I see.
So you can just like have this.
because this stick is constant.
Yeah. So if this linkage is anywhere in this range of motion, you're good. You can move.
Mm-hmm, mm-hmm.
But anywhere beyond this is a lock. And then also, if you're here,
this
you
is
can also
this is
move.
geometry, bro.
This is very basic geometry.
Basic geometry.
It's just
yeah.
trigonometry. There's nothing like complicated about it.
Yes.
Yeah.
Okay.
But there's a point where you lock, which is like these areas.
Yeah.
This is
okay.
in these linkage mechanisms. This is called like a branch defect.
branch defect.
Because you have multiple branches. You have this, like, if you assembled the mechanism here, this would be a range of motion.
Mhm.
If you assembled the mechanism here, this would be a range of motion. You have two branches, and they're not connected to each other. So it's a
Mhm.
branch defect.
Oh, okay.
Yeah.
They are not connected to.
Yeah, if you assemble your mechanism here, you can never get here. Right? You'll never be able to. So you have to assemble your mechanism differently, based on
Okay, I
which
get it.
motion you want. Yeah.
All right.
Anyways.
Okay, got it. Interesting. That is very actually interesting for mathematicians too. It should be interesting to them, right? Studying these curves.
So actually there is there are some frequency domain studies of these mechanisms.
Oh, okay.
Anyways, so one of the constraints is that it can't lock.
Mm-hmm.
So whatever mechanism
It
comes
can't
in-
lock, right? This
Yeah.
is the constraint.
This is a geometric constraint, but it gets complicated when you have a lot of joints.
Yes.
Because like many things can lock, and moving one of these joints can make the other one lock all of a sudden.
How many of these nodes do you want to add?
Up to 20 is what we cover in our work.
Okay.
Because you can keep adding more.
I was like at Andy's goodbye party, and there was a person who was doing juggling.
Yeah.
And he said like the most number, like Shannon in information theory, he used to do juggling too, and seems they are just nerd people, and he developed some mathematics of it. And do you know how many? Like, what is the most number of things?
Most number of objects you can juggle.
Yeah.
There's an actual limit to it.
Well, there is a guy who has the limit right now.
Oh, like
he has the record.
Oh no, but is there a mathematical number?
No, I don't know the mathematical.
Oh, I would say like maybe 15.
Yeah, actually, the guy is 11, but the thing is that each object you add, it's like exponential increase.
Yeah, it's the same thing here.
It's the same thing. It's very similar. It reminded me of that.
Yeah, I mean, the more your design space keeps growing, but it grows exponentially because, like, you add a joint, you can connect it to now n joints. You add that one, it's n plus one.
Dude,
combination.
this is an amazing.
It's a combination of 2 out of n.
Okay.
Right, the n grows, then space is exponential, or actually more than exponential.
So this covers up to 20.
So in my work, I have up to 20 joints. In practice, you can go as high as you want.
Oh, you can?
Yes, and there is a theoretical way of tracing any polynomial. Like if you can approximate your curve as a polynomial, you can come up with a theoretical mechanism.
How can this curve be polynomial?
Okay, imagine like you have a bunch of points here. You can
like
fit,
x and y are function of t, which polynomial function of t.
And you can fit like a polynomial of the nth degree. You can go as high as you need. The issue is those mechanisms involve like hundreds of
one
joints.
other thing, the guy is in math department at Harvard who does the juggling with 11.
Yeah.
All right.
Yeah. So yeah, what happens here is your space keeps increasing in size, but again, like the theoretical solutions would involve like 200, 300 joints.
Okay, which is
useless.
Yeah, useless. Okay.
Yeah, so you want to do it with some number of things, and if you want to see the solution to this specific one, that's the linkage mechanism that makes it.
How many is it? 5, 6.
Yeah, this is the curve that we wanted.
And you can add whatever number of.
You can. So you have different node types as well.
I see.
Like your problem is defined as a graph.
Oh, this is the one that created.
Yeah, this is the one that created it.
I see.
Yeah. And there's like the famous case of straight line mechanism. Because in steam engines, people wanted the straight line motion. So they wanted to come up with a mechanism, a linkage mechanism that can create a straight line.
All right.
So you have the rotation of the motor turns into a straight line.
Yeah,
that's what they wanted. There's a theoretical solution, and this is the theoretical solution.
Wow. Oh my god. But it is limited, right? It cannot go all the way because you have mathematical locks.
Yeah, I mean, depending on, like, you can increase the size of your mechanism to get whatever length you want. Right?
Yes, but this part is really straight.
It's actually
theoretically straight.
If you write the equation for it, it's a straight line.
Shit, this looks actually very beautiful. So this goes all the way.
Creates a rocking thing. And then
it has 2 grounds here.
Yeah.
That's crazy.
So the theoretical solution.
How do you find the solution to this kind of problem?
So this was theoretically written down. Like there's 3 different theoretical solutions to a straight line, and it's just people came up with it. It's just creative.
Heuristic. Like
not even like a specific heuristic. It's like sometimes you have this in math, right? Somebody says, "Oh, the solution to this PDE is this."
Is this? Where did you?
How did you come up with it?
God told me.
Yeah, exactly. God told me. It works, dude. What do you want from me?
Yeah.
That's kind of the same here.
No mathematician shares their scratch paper, right?
Even if they did, I don't know if that's
makes sense to other people.
It's not tractable to other problems necessarily.
Yeah.
Anyways, so there's like 3 different solutions to straight line. Whatever.
3 solutions to straight line.
There's other mechanisms. It doesn't look like this.
Okay.
The theoretical method that I talked about.
Dude, this is so cute actually. Like I give you this stuff and give me a curve. That in general.
Give me a mechanism, right?
Yeah, that's.
So your feasible space is massive.
Yeah.
There's so many different mechanisms that don't block and have 1 degree of freedom.
Yeah.
What you want is kind of a good feasible subset for a given curve.
Feasible subset for a given curve.
So I give you a curve.
Uh-huh.
Give me a few candidates basically that are feasible, that are likely to be able to trace that curve.
And what is your what is the error? How do you measure the error?
So you measure the similarity of the curves.
Like what is it?
Yeah. It's a good thing about these curves is that there's order. right? The order of the points is known. It's not a point cloud.
Yes.
The order of the points is known, so all you need to think about is permutation. Where's the start point, where's the end point, you know?
So no, because they give you a line, like not this straight line, the other one. Yes, this one. What is your starting point? Every point can be your starting point here.
Exactly. So there's n, depending on how many points you consider, there's n different permutations.
So you are looking at them like discrete points.
Yes, yeah. When you compare them in a discrete way. You don't compare their equations.
Oh, so you are not saying I have a metric how two continuous curves are close.
Yeah. This is a numerical curve.
All right.
It's not a, so the continuous
Is
equation.
there a continuous?
Yeah. I have the symbolic solver for this.
Okay.
The symbolic equation for this,
Mm.
even this, I'm not even getting more complicated than this. If you wanted to see the equation for this thing, it would take up like multiple chalkboards. Because the solution of this one
Alright.
relies on the solution of this one and the
Mm.
solution of this one. And the solution of this relies on the solution of this. So
Mm.
it's an equation based on this. So your first
Can
equation
we
is just
do-
a simple cosine,
Mm.
sine. This sine of
That's it. Yes.
sine of t
circle.
cosine of t.
Yes.
This becomes a function of like this. Let's call this f0.
Yes.
F1 is a function of f0, and then f2 is a function of f1, and then this one is a function of f1 and this one. This is a function of
Okay.
f1 and
I mean,
f0.
give me how do you, if you
So
want
this one becomes a function of all the f's.
for sure.
Yeah.
If you want to solve this system, how is
It's
the
a graph walk. You start with the known.
This one is known.
This one is known. The grounds are known.
So
Because the grounds, you know
let's
the
do
position.
that. Actually, I want to know how you solved it
Yeah. I
theoretically.
have, so let me pull up the paper. I guess then it becomes easier.
No, you can write it for us. I just
What-
want to know like the order. Is it like you end up with a system of equation you solve?
So it's a nonlinear equation of just a bunch of sines and cosines. But to show you what the graph walk looks like,
A graph walk. I want to know the graph.
yeah, I have a little
Dude,
illustration.
are these yours?
Yeah, those.
That looks like a massive paper.
It's a relatively long paper. I want to see the archive version down on PDF.
How is that related to IBM?
It's computational and AI.
okay.
There's AI.
Mm.
Yeah. How is it related to IBM? I don't know. Not directly.
38 pages, dude. That's not a
But yeah,
joke.
the graph walk is here. So the forward kinematic solver path.
Is it the same thing that we have already?
No, it's a smaller mechanism.
Oh, it is this guy. All right.
No, look at this thing.
Okay.
Look at the right side.
Oh, you have the arrows. All right.
Yeah, the arrows. So you got the actuator. You
Uh-huh.
have free joints, fixed joints, and initially known points.
Okay.
So the ground ones, you know their position.
They're
'Cause
known.
They're not moving.
This is also
The motor, you
cosine
know.
sine.
Yeah, the motor, you know. Okay. So from
What
a
is it?
trigonomic.
You don't. Oh, fixed joint is this. Fixed
Yeah,
joint
fixed joint is
All
free
right.
joints are. So trigonometrically speaking,
Mm-hmm.
if you know two known neighbors, and
Two
you know
known.
the length of the linkages, there's two arcs collide with each other. There's two
Yes,
possible.
we know
points.
the middle one.
You know two possible solutions, and if you know the initial solution and the initial position,
How do we know two initial tower two?
two arcs collide with each other twice, right? Like two circles.
Oh, like triangles. Yeah. Whenever we have two.
Yeah,
two
because you know the length of these linkages.
I see.
But if you also know the initial position,
What do we call this thing? Pargar in English?
protractor or no, protractor,
Protractor.
protractor. Oh no, this
No,
that
that-
measures the compass.
Is it? No.
Compass. Drawing tool. Yeah, compass.
Yes.
Yeah, compass.
No. Okay. Compass. Compass.
Compass. So yeah, if
I
you,
thought compass is the one that says very
yeah,
north.
that is also compass.
Oh, okay.
Yeah, the two.
So this is kind of playing with compasses. Kind of.
yeah, it is kind of like playing
Alright.
compasses, right? So if you know two of these and you know the length of the linkages,
Yes.
then you can find two possible ways they can.
Wait
be.
a second. Is this angle always constant?
No, they change.
No.
They're free to move. The joints, they do.
So
In fact,
once okay.
Look at the animation we had. Let's close this. The animation we have.
All right. Like for example. Oh yeah. The,
So
the
angles-
angles
this
change.
one closes
Angles
like
change.
this.
Wait a second, just to show that this, I mean this, between the two edges here,
that angle
the
changes.
angle changes. So okay, let's get back here.
Yeah.
Once we are moving, this one controls that.
So see, there's two knowns. You can find the third one. You get two possible solutions for them.
Okay, let me. Okay,
So, if you want the equation, I have the equation in the paper. It's a very simple equation. So this
I
is,
like the graph walk more.
yeah, I'll get to the graph walk, but I just want to show you like it's a very simple trigonomic equation. It's nothing. Yeah, there you go. Like xi of t. If you have two known neighbors of k and j, this becomes the equation. R phi is a rotation matrix phi.
This is the length of the
And phi
edge.
is this. Phi is a function.
Woo!
This
Okay.
is dependent on initial positions.
So this is xi is the node that we want to
At time t.
xj and xk we know where
We know where they are, yeah.
xi minus xj is constant
length of
because
the
the
linkage.
length of the linkage. And
this
R
is,
phi
R is a rotation matrix.
rotation matrix.
Rotation matrix,
The cosine
angle
minus
phi.
sine, sine cosine,
Yes,
right?
in 2D.
Alright.
And kj, you know the difference between kj at time t because they've been solved for.
they were been solved for.
Yeah, yeah, and you also know their distance,
Mm-hmm.
right?
Yes.
So you know their distance from each other.
Oh, it is time of function of t because those are moving.
Yeah,
As
yeah,
well.
it's
All
a
right.
time step. Yeah, and then
But you're saying
the
that
function
Oh,
phi-
of course.
the
It
f-
doesn't depend on the time at another time.
yeah, yeah, yeah. So the function phi is this, which is based on initial, so times 0 positions.
Yes.
Because that determines which of those intersections you want.
Yes, because we
Right.
have two options.
Yeah, yeah. And there's an inverse cosine here,
Mhm.
going into your rotation matrix. So it makes the equation a mess.
Yeah, this is big, but it looks very intuitive.
It's very, yeah, it's just trigonometry.
Yeah,
There's nothing,
that's trigonometry.
nothing special about
That was nice. And where is the graph walk?
The graph walk, so we have revised the paper to bring this further down. It's
Okay.
way too far from the equation. So
Oh, I see.
yeah, yeah. So the forward kinematic solid. So once you know these two positions,
We know. I know this. I know this.
you know, yeah. So you can find this one.
I know this
Step
also. Okay. Yeah, if you show on the with the pointer, that will be
Here,
great.
we can take the
So I know this.
yes.
I know this, and I know this because this is
This is
connected
actually it's a known thing.
These two I know.
So you can find one.
These two I can find one.
Yeah.
One
Once
I
you know
know.
one,
Two is obvious.
because it has two neighbors, right? You know the motor, you know one,
Yeah, and then three is
and then you can know.
perfect.
Yeah. So you just walk through the graph and you find your solution.
Is this a case that we cannot find a solution?
If it's a non-dyadic mechanism,
Dyadic?
non-dyadic.
What is non-dyadic?
So
By
dyadic-
two, like it's always been
Dyadic
two.
means that your mechanism resolves with a graph walk.
I see.
Non-dyadic means you have a complex kinematic loop.
Kinematic.
Yeah, complex kinematic
Alright.
meaning your solution. Okay, if I can draw it, I can show you better.
Yeah, do it.
It's still 1 degree of freedom. It
Mm.
can be solved.
Mm-hmm.
It's just that trigonometry alone is not enough anymore. Because
Oh, okay. You
yeah,
need
'cause
to
there's a-
do like
it's a
a
bigger
system of
bridge.
equations.
yes, so you need to
Alright.
build a system of equations for those larger loops.
Uh-huh.
Loops meaning, so this is a loop, for example. This is a ground joint.
Yeah.
You move up, you
Uh-huh.
move here, you move, come back here. So this is a loop you can solve.
From one fixed point to another.
Yeah, yeah, yeah. Or even like, yeah, so like from one known to another known.
Alright.
Yeah, so those loops you can solve with a system of equations.
That have no connection to the anything outside, something like that?
Yeah, because you know the lengths, right? So you have known information, you have priors.
Okay.
Yeah, but if...
Wait a second. Are you saying that if we didn't have this fixed point,
Mhm.
and if it was just these two?
Well,
and-
that would be more than 1 degree of freedom. You need to, if it has to be 1 degree of freedom. Meaning that the number of
No,
constraints...
I have only like 2, 3, and these two.
Uh-huh.
It is okay, right?
Yeah, there you can solve this. That's a dyadic mechanism.
It is dyadic?
Yeah.
No, how can I have 3?
Wait, actually, that's not 1 degree of freedom.
It's complicated.
No, that's not 1 degree of freedom problem. That's a 2 degree of freedom problem.
What is 2 degree of freedom?
The relative angles between 2 and 3 are free to be anything, really. Like regardless
How
of
do
what
you-
this is.
Mm,
Look, it's hanging. This
yes.
can rotate, but they can rotate relative to that, no problem.
I see. Okay.
You can
okay.
solve that.
How do you, from the beginning, how do you set that it is one?
That's one of the constraints. If you look at the
Yeah, it is the constraint, but how do you look at the graph and say it is 1 degree of freedom and what if it is?
There's an equation for it. it's like the number of free joints.
Mm-hmm.
There's two things you need to solve for them in space,
Mm-hmm.
and each linkage is a constraint.
Mm-hmm.
So it's the number of free joints times 2. It's a very simple thing. It's like,
Alright. It's just like a linear algebra thing that we have this
yeah,
number
but you
of
can see like
constraints.
the constraint is DOF of the mechanism has to be 1.
I see. So we have this many constraints, we have this many points. So, okay. Alright.
This becomes like it's a large feasible space.
Mm-hmm.
So you want to come up with solutions that are like the subset of feasible solutions that are likely to be able to generate these curves.
Mm-hmm.
Then you saw the solver, right?
And one other question I had was like, how do you measure the similarity or difference between curves?
Yeah, so we do it numerically. You just sample endpoints of this curve,
Uh-huh.
and then you use. Let me show you where that equation is. No, these are the loss functions. Yeah, here. So this is endpoints that you have.
And then you compare their mutual distance.
Yeah, it's just like this is the norm of the distance between each of them, but then you don't know the permutation.
Exactly. How do you say this point of this
You
curve?
try all possible permutations, you take the minimum. If you look, it's minimum of O1 in O, big O1. Look, if you look at the notation here, it's the minimum.
Okay.
So all possible, it's not expensive. This is a very cheap
Like
thing.
all the
computational.
permutation is not expensive?
No, computationally it's not expensive.
Why do you compare on all permutation? Why don't you just go
Well,
over?
I don't know the optimal permutation. I don't know the optimal.
But you know the direction of the curve, right?
We have curvature information, yeah.
So you have the direction of the curve.
Mm-hmm.
Where is the? Okay, yeah. So you have the direction of the curve, right? You know this curve. Like if you have point I here, you know I plus 1 is here.
Yeah.
So you don't need to go, and you have this curve here that you want to see how close these two are, right? And its point I is like this, and this is, you just need to have the starting point.
Yeah. So there's n possible
N
permutations.
possible.
Yeah.
It's not n
Combination.
factorial.
It's not a combination. Yeah. It's not a
N,
factorial.
n factorial
Because
would be
you know
huge.
order. Yeah. Otherwise that would be computationally insane.
Insane, right?
Yeah. No.
Okay.
This is computationally practical because you have order information.
Yes.
So you have only n possible
N, okay.
permutations. Yeah. All possible permutations are only n. Yeah.
Wait, okay, but one other thing. You have these two curves on the, let's go back here. You have these two curves.
Yeah.
You say like this is at this point like this is x, this is
Talking
y.
about normalizing them in space.
Yeah.
Yeah, we do that with.
How do you do that?
It is a theoretical way. It's Procustis analysis. It's called Procustis analysis for comparing two curves.
Mm-hmm.
And the way it's done is, I can go back up. Oh yeah, here we go.
Dude, this is very mathematics.
Yeah, so normalized is minus the mean.
Oh, mean of all of these points.
Yeah, and then this is the root mean squared error, root mean squared distance from the mean for scaling. So the scale and position is normalized. Rotation.
No rotation, we don't.
We don't. Okay, so that's another part. It's like
All right.
that's also optimized for.
It is.
Yeah.
Who did this kind of work? Are they mechanical engineers or mathematicians?
Procustis analysis was done by mathematicians. I didn't put the equation of the rotation, but if you know association, basically if you know in curve 1, which point, like curve 1i is associated with curve 2j.
Show it on us.
Yeah, this is all mathematics and like basic geometry. Okay. Look, let's say we got like this curve, like that, and we want to try to match it to a curve that's similar but not quite the same. Let's say.
If it is the same, how do you do that?
Okay, let's say it's the same, but you don't know the order.
Yeah. Okay.
Okay, so you got this point here. This is called curve 1. This is called curve 2.
Okay.
This is I, and then J. If you know the association, basically if you have a mapping from 1 to 2, saying, let's say CI 1 and CJ 2 are associated with each other. Right. If
2
you-
is the number of curve.
Yeah, 2 is a curve number.
Okay.
You flip the indexes, whatever. If you know this association,
Mm-hmm.
then if you write the equation of the rotations with respect, if you know all the point associations.
Okay, one thing. Once I have one mapping from this to this, I can have n mapping from this to this. That is just changing the.
Yeah, there's n possible permutations. We established that,
Yes.
right? What we didn't establish is like how do we find the rotation? We found the scale, we
Yes.
found the position in space, so we can
Yes.
normalize for those. How do we find the relative rotation between these? Well, if you know associations, if you know which point in 1 and which point in 2 are associated with each other,
Yes.
there's an
Like
inverse
this,
tan.
this I, let's assume I and J are the.
Yeah, I and J are the associated things. Then you have, like xi, j.
Well, actually, this is not a good photo for a rotation.
Yeah.
Maybe you can cut it and rotate it. You can. That's fine. You cannot rotate.
Should be there somewhere.
At least do 90 degrees rotation.
Forward, backward. Okay, you know what? I can draw it again.
Change the style. Let us change the style.
Like, let's say,
Draw like a maybe oval shape that is. Oh, that's perfect actually. Okay.
there you go. Okay, it's like a 90-degree rotation.
Yes.
We want like this, like 90 degrees here.
Yes,
Because
exactly.
we're trying to find
Like
that.
the J is here.
Yeah, like
Why don't you call both of them I?
call them I.
Both of them are I,
Yeah.
right? Okay.
Yeah. So if you write the equation of the distances between x1 minus x2.
Once they are centered.
Yeah, I and j. Well, not once they're centered.
Once they
You
are,
have the raw value.
what
You
is
have
it?
them like randomly positioned in space.
Like this.
You're trying to match it. Yeah.
Like this.
Yeah. So once you did the first 2 steps of stochastic analysis, we just
Mm.
scaled them and positioned them in space.
So they are centered now.
Yeah. Now they're centered.
They are centered, but like,
And scaled the same, so that their scale is the same too, right?
Oh.
We divided by the root of the sum of distances, like
yeah.
square root
So
of the sum
we
of the-
we also had the scale. I
Yeah.
thought we are the same size from the beginning, but okay, that's also something.
We can adjust.
Yeah,
this.
we can
Those are
adjust.
theoretically like
So
known.
now let's assume they are like same scale.
Yeah, yeah, yeah.
We have something. Copy. We have something like this.
Yeah, yeah. But we want to find the rotation.
Let me also make it red. Change the style. So we have something like this. These two curves. We want to make.
We want
so-
to find that rotation. You write down the equation for the distance, which is what we have here.
All right.
If you write this equation down,
The I and J.
yeah,
Okay.
with some unknown rotation, like let's some r theta. We want to find theta.
Uh huh.
And then you say I want to minimize this with respect to theta. You can actually solve this is a convex problem, and the solution is in closed
This is
form.
a convex problem.
It's a convex problem as a solution. It's it's just it's a parabola. It's not. It's a L2 norm.
Quadratic form.
Yeah, quadratic form.
Alright,
It's
okay.
nothing. It's convex.
Mm.
Find gradient 0. Find you formulate the gradient.
You
equal to
probably
0.
can have it.
It's an
closed
inverse
form.
tan. Yeah, it's a closed form. It's very
Alright.
simple. Yeah, it's inverse
All
tan.
right. Okay.
Inverse tan of something with it's like a sum of positions. Inverse tan of that. Whatever. That you can find that. Like if you know associations of points, the thing you don't know is the association.
So I think only thing that if it was not discrete, we could say it's like integral, something like.
If it wasn't discrete, then you would have the actual curves, like the actual function.
Yeah.
Then we have a function of t. You need to find t naught, which is t0 that aligns them.
Zero. That is the
So it will
biggest-
be f1 of t, f2 of t minus t0.
Yes.
You gotta find t0, and then you also would have to find the scale and positioning of these.
All right. Good.
But the positioning is easy to find with an integral,
Mhm.
and the scale is also similarly easy to find with an integral.
Mhm.
This all the sums will turn into integrals basically if you have.
Yes, all the sums then.
Yeah, but these are parametric curves.
Damn, this
of
was really cool.
functions.
All right. So let's.
Yeah, it's just fun math. But it's like simple. It's like high school level math. There's
Alright.
nothing.
Let's jump back to our model and everything. All right. Well, okay. So we have a curve. They give you a curve. Can you make it?
Can you make a mechanism that traces it?
Yeah.
Yeah.
Or give us the mechanism that this error is the minimum.
Oh yeah, it minimizes the error.
Yes.
Minimize the error given constraints are don't lock
Mm-hmm.
and DOF1. DOF1 is easy.
DOF1?
Degree of freedom.
Degree of freedom.
Degree of freedom 1, that's easy.
Mm.
Not locking, it gets very complicated as you have more curves.
More curves, alright.
And we have a
More
little
knots.
illustration of that in the paper too, of like what it's a nonlinear thing, right? And they keep stacking these functions on top of each other. So the feasible space is.
Let me see. Oh shoot, sorry. What are these? Oh, you
Like,
are
we're tracing
alphabet.
the alphabet, yeah. This is the mechanism of traces.
What are these gray areas?
Yeah, so this is
Lock
feasible,
space.
feasible regions and infeasible regions
Ah.
for this node,
Uh-huh.
for this one node.
Okay.
If you move any of these nodes in their feasible region, the feasible region of the other nodes change.
Of course.
Yeah, so
Yes.
you got this kind of, from an optimization perspective, it's a mess.
Yes, it's very like you have a like for example 2-dimensional and there are like areas of it you cannot go.
Like literally everything is kind of
So
free.
gray areas are the feasible.
Yeah, feasible region, red areas.
Pink
are-
is okay.
Infeasible,
Infeasible.
yeah.
Ah, that's actually infeasible is very big, and it doesn't.
But depending
look-
on which of these nodes you select to see the feasible region, it changes the
Yes,
shape
of
and
course.
whatever.
and it doesn't look convex or connected.
If they're
or
discontinuous, non-convex, and
Yeah.
non-linear.
exactly.
Yeah. So all the bad things
All the
together.
bad things.
Yeah.
Some topologies should go.
Yeah.
And these are all the curves that.
These are test curves that were
these
not
are-
in the data set that it generated mechanisms for. And they're basically perfect.
Wow, what is this one?
Yeah, there's a mechanism that goes like this, and then there's another.
Oh, it cuts itself.
Yeah, you can have self-intersecting
I
curves.
see. Okay, like this one, but
Yeah,
like it's the fetus growing up, something like.
yeah.
And what is this?
These are
one?
hand-drawn test curves. These are curves that are tested in the literature. That's why we have them. They're kinda
Oh,
ugly.
okay.
It's what we can compare against.
Okay.
Yeah, these are ugly curves, but yeah. And we also have the alphabet
one
test.
application of this was the straight
So
line.
straight line is like the one that's kind of been solved, but like in the real world, if you want, for example, specifically repeatable motion,
Uh-huh.
like
Robots. In a-
robots. So kinematic design of robots is very hard
Mhm.
because it's not just a motion you want.
Emotion matters.
Yeah, it's not just motion. It's also like, for example, if you're talking a humanoid robot,
Uh-huh.
I want to design a mechanism for its arm
Mhm.
that can allow a certain type of motion happening. Can allow a space of possible motions.
Mhm.
Like there's a manifold of things it can do.
Mhm.
Right. So your objective is no longer a curve there.
Mhm.
Your objective is, I want to be able to do these things,
Mhm.
these kinds of motions. How do I design this mechanism?
So instead of curves, we have kind of motion.
We have like a space of, it's a little more abstract,
So we have a space of all the curves we want.
or all the motions we want. Like, because in 3D,
Fast.
in 3D
slow.
you have like 3 rotation,
Yes.
so you have 6 degrees of freedom, right?
Yes.
Like you want, for example, a region, you want the region of possible motion. Like there's this cloud in space that I want to be
Yes.
able to move around in.
Wherever in that space
yeah.
I want to be able to.
I want to be
go.
able to move there, and then there's a motion, which is that I want to be able to have like a certain speed, a certain angle
Oh,
everywhere.
speed and angle.
Yeah, so
of course.
this space that you define with that is a more abstract space.
Mhm.
But what we're trying to do here is to come up with a way to do this very difficult combinatorial bullshit problem.
Why is it combinatorial?
We have to come up with this mechanism thing, the graph. The graph topology is
Oh.
combinatorial.
Okay, yeah.
Yeah, yeah. That's why the feasible space is so massive and it's just hard to do. Because the continuous. So the funny thing is, you saw the equations, right? They're all
Mhm.
smooth.
Yes.
They're all differentiable.
Yes, yes.
If you have a good feasible subset,
Yes.
you can just like find local minima with the Haitian
Mm-hmm. Yes.
in 2 steps.
Yes,
You
yes.
find it with so the thing that's hard is what's the feasible subset,
Mm-hmm.
because that space is massive.
Massive.
But then once you have the feasible subset, you can run optimization and find it.
Yeah.
Well, the Haitian is not. It's too big. It's shitty. But what you can do is BFGS.
BFGS.
And BFGS is this algorithm, Broyden, Frood, whatever.
Freud.
There's
yeah.
There's 4 people who made up that algorithm. It's a way to approximate the Haitian without actually computing it,
Oh, okay.
because computing it is
Time.
Yeah, not feasible.
Alright.
Yeah, so you approximate the Haitian using that. That's the mixed linear linear program for manufacturability.
How many people were in this part? You were the
I'm the only one that wrote the whole thing and did the whole thing.
Oh.
Everybody else did nothing for this.
It's recorded now.
That's okay. They know that. Like, I mean, okay, no. Okay, they did give me guidance,
Okay.
but like hands-on, no, nothing.
Dude, that's fucking paper, bro.
Yeah. So.
Faiz, we know you.
Faiz Ahmed.
Alright.
Yeah, he's my PI. Yeah,
And there was a team, 2 people.
three people from
3 people. Why is IBM is interested in it because of robotics?
Not robotics. IBM wants what they call the hybrid generative models. We have a generative model,
Like
ML model, like ChatGPT,
All right.
but these are not precise. For engineering design, you want like very precise continuous values and so on.
Okay.
So they were interested in combining optimization with deep learning. And
Jeez. Combining optimization with
deep learning, or not optimization, but like precise design methods, or like precision methods, which is a computation, like conventional computation.
Okay, wait a second. What will ChatGPT do if you give it this problem to ChatGPT? Or
It's too abstract.
well,
Honestly,
what
for
was the
ChatGPT.
title again?
Oh, what?
Precision attention models. You said?
No, precision generative.
Precision generative models. If you give this problem to a generative model, what would it do?
Okay, I can show you what happens. So here we combine optimization with, as I said, finding local minima is easy.
Mm-hmm.
What I want my generative model to do is give me the feasible subset.
Okay.
It's not going to be good,
Mm-hmm.
but it's going to be something. And then you run, it's because it's not an unconstrained, BFGS is an unconstrained optimization algorithm.
Mm-hmm.
It's a modified BFGS. Who cares? Those details are not that important. I don't care about heuristics. I'm not interested in discussing heuristics.
Jeez, alright, bitch. Okay. Go ahead.
Yeah. So there's this model that learns how to map mechanisms to curves. We also do partial curves. So if it's not a closed curve.
Dude, you really put some effort in this paper. Look at all these colors and
Yeah, I
stuff.
always make the figures with Illustrator.
How do you make them?
Adobe Illustrator.
Adobe.
Yeah, Illustrator.
Alright.
Oh, by the way, have you seen the Adobe Illustrator AI?
No.
Give it text, it will give you vector.
Really?
Like vector like this. Like these are not, this is not an image. You can zoom in as much as you want.
Jeez, it's drawing.
Yeah, it's an actual drawing.
Oh my
You
god.
can zoom in and it will like render it for you. Like you could even select text if you want.
You exploited whatever MIT could give you.
Yeah, I maxed out my MIT gear.
I didn't updated my Microsoft since 2019.
Yeah, no, I make the figures in Illustrator. Yeah, well, anyways.
How do you find? Okay, one thing I always impressed. Amin knows so much about everything. How do you first time got to know about Adobe?
I just messed around with the thing until I learned it, and then I
Okay.
watched some YouTube videos or something. Yeah, but
Yeah.
all of these images are vectors. They're not pictures. Yeah.
so
you can zoom
Adobe
in.
is doing really good job.
Yeah. All the curves and everything that's like visual, even these that I get out of Python, I get them as the SVGs, like vectors, and I put them in the paper. So, yeah,
Damn, I want to learn that.
it's not because images
I have
always
a lot
breaks
of
because you zoom in and then it becomes garbage
yeah.
if you zoom in enough.
Well, the data you get from Python is discrete, anyways.
Yeah, but like these lines, you can render them at any resolution still. Like if it's a curve, you can render it.
Oh, I see. Okay.
Yeah, of course, it's discrete. I mean, eventually you zoom and you see the little lines.
Yes. Okay. Damn. Okay. All right.
Anyways, yeah, but that's the hard part of that is
So okay, we were saying generative AI.
yes, generative. The generative part is I want the feasible subset to be generated by this
Yeah.
AI, which it can do a good job of. But then I do so once I have this,
Precise generative AI.
yeah. So the precision comes with like traditional methods like BFGS, like gradient-based optimization.
BFGS gives you the precision.
Like if you give me your thing and maybe it's not good, like okay, let's go back here. Let's say I move this a little bit, like because these continuous values define the position. Right. Okay, it's locked.
Wow.
Very easy to lock.
We couldn't move it a bit.
Yeah, okay, let's put this here. Okay, maybe the AI gives me this. Like
Okay.
this is not very good, right? This is not a good curve.
Yes.
But my BFGS, given this, BFGS probably will just find. Like,
Wait.
it's-
What is BFGS?
let's say.
What does it do? Okay. It gives you the initial points.
No, it's a gradient-based optimization, iterative gradient-based optimization.
What are you?
Boyd Fletcher Goldfarb-Shannon algorithm.
All right.
You have objective function is the same, or the
So
distance.
Mm-hmm.
The distance between the curves, that's our objective function.
Yeah.
And the parameters we optimize for are the position of these joints in space.
Mm-hmm. So once you use BFGS, your algorithm becomes precision generative AI.
Because the BFGS is using the simulation, which is precise.
Wait a second. Let me get back. Okay, you want this curve, and your system comes up with.
It gives me a few candidates
with these nodes.
that are it gives me a few mechanisms.
Okay.
It generates
One is enough, right?
Well, one solution is enough.
One solution
But
is.
the AI is not always good at this, so it gives
Uh-huh.
me a bunch of candidates, and I
Okay.
can quickly find the local minimums of these. Like, okay, bi-level optimization.
So it gives you initial point.
Yes,
Okay.
bi-level optimization. Your low level has a huge feasible subset.
Mm-hmm.
You can run the high level on all of your feasible subset,
Mm.
and you'll find the global best solution.
Ah.
Point is that feasible subset is fucking
Mm.
infinite.
I see.
Yeah. So what I want my
So
AI
you
to do.
broke your optimization in two steps.
Yeah, it's bi-level optimization.
Bi means two. Okay. Okay.
Bi-level optimization.
I see. Okay. So the first part on AI, give me a good feasible space. Then the second part
Is just conventional optimization.
conventional optimization.
Yeah.
Mhm.
And the conventional optimization, this is not an unconstrained problem. BFGS is an unconstrained optimization approach.
Mm-hmm.
So we just do some modifications, but it's heuristics. Not, I didn't even mention it in the paper. I just said modify BFGS.
All right.
Because I don't care about heuristics. Yeah. Yeah, so it gives you, so the live demo I had is you could draw whatever curve you wanted and get a mechanism.
That's crazy.
Yeah, and-
Because here we just had the given nodes, right?
Yeah. Those are like pre-calculated for that one. So we design AI that
This was actually a creative paper. Okay, it was a good, nice optimization paper at least.
Yeah. I think the goal wasn't to solve this problem.
Mm-hmm.
The goal was to show that this problem you can't solve with optimization.
This is not a. I don't know. Okay, this is a problem. Did you build the problem yourself?
There were other people who had before explored
Uh-huh.
this, not that much.
Like have
Yeah,
give
yeah.
me a curve and I
I wanted to create models that can do this kind of thing
Mm-hmm.
that traditional optimization can't do. So we have these like prior works.
Okay.
They use like
Oh,
traditional
they are
optimization.
actually very recent too.
Well, yeah. So mixed integer nonlinear program
Ooh, okay.
by Panatau. So you see the maximum number of joints they can get to is 7, because if you go beyond that it becomes
NP hard and short.
it's already basically that, but yeah, it's fucked up anyway. So it takes
Um,
them 36,000 seconds, so a day and a bit,
All right.
like
And
a day and a half to solve.
the same year, the same person.
It's the same paper.
Oh, the
It's
same.
mixed integer conic programming,
Conic.
so you relax some of the things, so some of the nonlinearity.
How do you write conic? C-O-N?
Yeah, conic.
What does conic mean? Iconic means.
Cones like.
Okay, conic. All right.
Yeah,
All right.
yeah. So you relax your equations.
Okay.
So they're no longer fully nonlinear. So
Mhm.
there's some, and then you run that. Also, again, combinatorial space is always the problem. And then it takes them like a little more than a day instead of a day and a
Mhm.
half. And then these GCP Hollow methods, these are reinforcement learning.
Wait, you write your papers using overleaf?
Yeah.
Okay, go ahead.
Yeah. So GCP Hollow, Fogel, Senetal. This is reinforcement learning.
Okay.
You know about reinforcement learning, right? Like
Yes. Yes.
So they also again, like reinforcement learning also has to explore the space.
Uh-huh.
It's like, okay, they can go up to 11 joints.
Mm-hmm.
Takes them around 40 minutes ish.
Okay.
So it's like
40 minutes join. So as long as the number of joints is below 11, this is time. It's not
Yeah.
like it's not about the
Well,
cap.
depending on your problem, it may find a solution that is good enough, whatever threshold you have for
Mhm.
good enough, that is faster than this. But this was their average time.
Mm-hmm.
And then in our case, actually this time has been updated. It's not 75 seconds. It's 15 seconds.
What the fuck? 15 seconds on their minutes?
They're in 40 minutes, yeah. And
They do the same thing?
same thing, and you can see the performance as well. This is my performance
Bro, that was
compared
that's a massive
to
paper.
their performance.
Okay,
Order of magnitude.
who are these?
This is if you limit the number of joints.
Okay.
The performance
okay.
gets worse.
This is
This is performance of up to 20.
okay.
Also, this has been updated. Again, like this paper.
You
this is
did
old.
this stuff or
No,
they
this
give
is
it
their.
to you?
This is their paper.
But the mean, did you
Yeah, yeah,
compute it or no? They give it.
They give me every single one of these numbers.
Ah, okay,
I can calculate an average.
Dude, this is
So,
massive improvement.
Yeah, order of magnitude.
Right?
Sometimes 2 orders of magnitude. Yeah.
Also, it was both in time and also the.
Time is a bigger order, like 2 order of magnitude than time.
Definitely. Where was it? It was
Uh,
like 40 minutes. It came 15 seconds.
15 seconds, yeah. So this is again updated. The new version is 15 seconds. But it was 2,500 seconds to 15 seconds.
So time fucking
2 orders of magnitude.
2 orders of magnitude.
Performance 1 order of magnitude.
Performance 1. That is massive improvement.
Yeah. So, anyways,
So what was the technology difference that you used?
so they are basically just doing optimization. Reinforcement learning is a form of optimization.
Oh, they didn't do that bi-level.
They didn't do bi-level. They also didn't do generative models to get their subset. So the generative model part is the acceleration. The bi-level is the accuracy.
Yes.
Um,
The time comes from the generative.
Because it gives you the subset like this.
And
The
then
reinforcement
accuracy
learning-
is easy.
Yeah, so if you have a good...
They don't have accurate result because they
No.
put a lot of their resources
No,
on
mixed
the-
integer linear programming and conic programming, they do have accurate results. They
Okay,
do the gradient-based part.
I see.
They
But they use a lot of their resources on doing a bigger space. Maybe that cost them in their accuracy as well.
So mixed integer conic programming at least comes with a guarantee.
Okay.
Yeah, that you have covered your space.
Okay.
But it's because it's relaxed, you actually haven't covered your space.
Wow. All right. So that's great.
Yeah.
And the thing is that you are saying any curve.
Any curve, yeah, any curve. And also you can limit the number of joints. This is something you can give you can tell your generative model, I want only 8 joints, and it will give you only 8
So
joints.
you developed the generative model?
Yeah, we trained it. And also the architecture is a little different. Like some parts of this, like we take into account, like you see this architecture, the graph hop model.
Mm-hmm.
You use attention mechanism for, so graph neural networks,
So it's not like you use ChatGPT. You built the ChatGPT.
Yeah, we built the model ourselves. Like it's built on prior work. Like GIN, graph isomorphism networks, is a thing that existed. Dot product self-attention existed. Like these are not new innovations in terms of architecture, but putting them together in this way, I guess it's new.
Dude, actually, the other day I was don't go. We were talking in our group meeting about, like, you have ChatGPT, which is designed for language,
Yeah.
human language, and you can use that trained model to stabilize the reverse pendulum,
Yeah. Mm-hmm.
which is crazy because that data is human language. This is like a mechanical thing.
Yeah, but it writes code for that.
Oh, it writes code.
It doesn't like give you human input.
I thought he just sets the weight based on the data he learned from human data.
Usually when you ask for mathematical things, ChatGPT will tell you I ran this
No,
code.
I think once, the person who was presenting, he said like if you have a neural network, you want to compute these coefficients, right?
Mm-hmm.
So for ChatGPT, they did it for based on the human language.
Mm-hmm. Yes, they use the human data.
He says these coefficients are working for reverse pendulum.
Okay, so they gave ChatGPT the problem.
Mm-hmm.
I want to solve a reverse pendulum.
No.
What did it say to ChatGPT? How did he get anything out of ChatGPT then?
Okay, it's not ChatGPT, but it's LLM.
Okay, so this still has to be language. Like LLM takes in as input some tokens.
Mm-hmm.
It's a vision language model that it takes also images.
So wait, tell me, how do you do that if you wanna give an LLM a reverse pendulum?
I have to describe the problem to the LLM in human language.
Oh, you say they did it in human language.
Yeah, they said I want to solve the inverse pendulum problem.
If that's it, it's not very impressive.
It's not impressive. Yeah, and
Yeah.
most ChatGPT experiments or like LLM experiments are not impressive to me.
Okay, so I got that wrong, or maybe I have to check with.
Yeah, I
him
have to
again.
check with them, see exactly what I mean, because
Yeah.
you can give them an image of the pendulum too.
Yeah.
That also
I
works.
was thinking, what about just giving all the sensors of the pendulum to the?
Raw, just say don't give any context about the sensors.
Yeah, no number. This is what I want. These are the numbers from
So how do you describe what you want?
speed 0, like sensors final speed should be 0. It should be at the top. So.
But you have to describe your setup.
Okay, what if the input to the LLM is just these numbers from sensors?
Yeah, but what do you expect the LLM to give you from that? The LLM will be like, thank you.
No. Okay, output of LLM should be the speed of this thing that moves so that the sensors turns to be 0.
Sure, but how does the LLM know the context of your problem? Like, you give it a bunch of numbers. What is it supposed to do?
Exactly. Play around, like reinforcement learning, play around with those numbers.
Until what? It
Until
can infer something random from those numbers too. It can hallucinate.
Well, it is. They are saying that this is working.
No, I think what they were saying is that they described their setup, gave those numbers, and asked ChatGPT to give a response.
Okay, I have to check. If it is this that you're saying, that will be.
I don't see how you give no context information to something and it gets meaningful output out of that.
Well, isn't it reinforcement learning?
But reinforcement learning comes with an objective. It's like optimization.
Well,
reinforcement learning is just
objective is clear here. Objective is that you have the option to move this
reinforcement
thing.
learning, you need a feedback.
Well, we have a feedback. Sensors are the feedback. Data is coming.
Tell me this. So basic reinforcement learning. How do you train a reinforcement learning model? How do you train it?
Okay, I don't know that much about reinforcement.
No. But I want to know what you think it is. Because it's a very simple idea, right?
Okay, you have some control, right? You can move this thing and see how.
So you have an output space.
Yes.
Which
and
is
how,
control.
Yeah, and how the sensors.
So that's your input space. It's the sensors.
Yes.
And your output is your controllable
moving.
Yeah.
And the sensors probably are on the panel.
Whatever. That's your input. Input is sensors.
Exactly.
Output is adjustable variable. How do you train this? How do you train a model that takes as input?
Okay, the thing is that they didn't train it. They didn't train it based on this. I think the whole thing was that, okay, this is mind-blowing for me, mind-blowing for me in that time was that those coefficients, the model was already trained on human language.
Yeah.
And they used this model for this thing.
Yeah.
And it worked.
Yeah, they had to give it context.
Okay.
There's no way. So reinforcement learning, what you do is you have your input space, your output space, you have some machine learning, there's some neural network. And the way you train it is you let it give random inputs.
Tries and
then based on the performance, that performance can be abstract, but it's a known objective.
yes.
You tell the model how it did.
Yes.
And that's how you train it. So without that performance, which is the description of your problem, how does it learn anything?
Yeah.
Because it can't infer the objective.
Okay, actually now for me the magic was that okay, we didn't even
The magic for you was that it inferred the objective from.
No, not the inferred. The objective was given to that,
Okay.
but they were not training a model. The model was already built based on LLM.
Yeah, so you can do it if you tell ChatGPT what my objective is and give the sensor data. It will tell you what to do.
No, that's obvious. That's not interesting.
Yeah.
What I had in mind is that we have this LLM.
Yeah.
We give it bunch of numbers from the sensors, and it gives us the right move without trying to find out that. I don't know. I need to check with them what was it then, because I don't know much about LLMs, and they were saying something. All right. So this part were already built. What was? Did you add anything?
Yeah,
or
yeah.
like?
So this attention mechanism, combining the attention mechanism with the graph neural network, is. So we argued that you remember the solver is a graph walk. It walks through the graph based on known neighbors.
Yeah.
So each node requires a different number of steps to be solved, right?
Okay.
The node 1 was solved in one step.
Yes.
Node 2.
Okay.
Graph neural networks, the way they work is there's a neural network that goes like node 1 and node 2 are connected. The neural network takes the features in node 1, it can be a vector, processes them with the neural network, becomes another vector, sends it to the neighbors of this node. So node 1 goes through, so do you know Google's search sorting mechanism?
Oh, this is about the accuracy part.
No, this is about the architecture here.
But this is about architecture. All right.
So yeah, a graph neural network.
How do you know how many nodes do you have then?
You don't know how many nodes you have.
Oh, okay, you're finding it.
No, this is not the generative model.
Okay.
This is a different thing. This is processing. This is about like how do you define the graph?
Okay.
Like how do you process a graph neural? How do you process a mechanism into a fixed length embedding?
All right.
I give you a graph that describes a mechanism. You give me a vector.
Okay.
That's what I want.
Mm-hmm.
Yeah, so this model was kind of new.
Mm-hmm.
This is the new architecture that we came up with that.
Okay.
The argument is that you don't know how many hops you need. You don't know how many messages you need to
Mhm.
solve. So we'll use a attention mechanism, which is what's used in transformers like GPT and stuff.
How many what are the hops from 1 to 2 to on the graph one?
So every time, so a graph neural network works by message passing.
Mm-hmm.
What it is each node has some features. It sends a message to all its neighbors,
Mm-hmm.
and every node receives all their messages and accumulates them into something.
Mm-hmm.
Now, every layer of graph neural network you have, your
Mhm.
receptive field increases.
Mm-hmm.
Right? Because the first time you you have a neural network, you get message only from your immediate neighbors.
Yes.
But in that same step, your neighbors got messages from their neighbors.
Yes.
So next time they send information, you have information about 2 people away from
Okay.
you.
Okay.
So in the solver, we don't know how many people away from us we need information from.
Mm-hmm.
So what we do is we say, okay, we'll run like up to 16 messages. Like we'll
How
send
big are these graph neural networks?
pretty big,
Okay.
a few million parameters.
Okay.
Yeah. They send in messages. So
Mhm.
whatever we say, okay, 16. We say
Mhm.
16 layers.
Mm-hmm.
That's more than enough to solve every mechanism in the up to 20.
Mm-hmm.
We don't know how many, so we'll try to learn that. Like we'll let the model infer that itself. So that's the attention mechanism.
So one other question. You were mechanical engineer when you were undergrad.
Yeah, but all the courses I've taken since course 6.
Oh, okay.
Except
so
with the
that's
exception
how,
of a few. Yeah, I learned these
from your
my
courses.
research, yeah. I didn't do optimization in my undergrad. Undergrad I was doing fluid mechanics and springs.
Mm. So who changed? Your advisor told you to
I
take
wanted to do machine learning.
machine learning.
Yeah,
All
so
right.
that I came to my advisor because
Mm.
he was doing machine learning.
Okay, okay. Because you knew that it is a hot topic right now.
It was a hot topic, and I was interested in it.
I see,
Like
I
personally
see.
interested in it, and it was a hot topic. So I was like, okay, I want to work on this. And I did not want to switch majors. I didn't want to do ECS.
I see.
I wanted to still be a mechanical engineer, but apply AI to mechanical engineering problems. That was the point.
That's actually okay. These curves are beautiful. I
These
don't-
curves are like, a weird mixture of cosine, sines, and inverse cosines.
One thing about mechanical engineer I like, and we talked at the beginning, was it's kind of relatable. You can see.
Yeah, it's physical.
Yeah, it's physical.
And the other demo, the other thing I wanted to talk about today that I guess we didn't get to
Oh, okay. What is this?
was this is topology optimization of structures.
Topology.
So you see the structure that it's coming up with?
Wait a second. Topology optimization of the structures.
Yeah.
What is a structure?
Yeah, okay.
What is
So
topology
this is
of
good
this?
because I have intro slides for this. Topology optimization, quick back. Yeah. Okay, so let's say you have this space, right?
Okay.
Like this is your design space. You want to distribute material in this space.
Distribute, you mean you cut something from it?
Cut
or-
something or like put material where it makes sense.
What do you mean? Put from
Just give me a
outside to it?
second.
Is it like David's sculpture that they said I saw it in the raw rock and then I cut it?
Okay, so this is the kind of the space.
Uh-huh.
You can, I don't know how familiar you are with finite element analysis. But what it is you have some sort of partial differential equation that describes your physics.
Okay.
To solve that, you use a numerically solve it.
Mm-hmm.
To numerically solve, you discretize your space.
Yes.
You discretize your space into some mesh.
Integral. All right.
Yeah, yeah.
Okay.
Integral, but numerically.
Okay.
That's exactly what finite element, by the way, is. It's just
Right.
integrating over known shapes.
Okay.
So there's the shape. You have some shape to your domain.
Mhm.
Let's say this is the physical domain you want to work in.
Which is a cube here.
Here it's like a prismatic.
Charismatic.
No. It's a rectangular prism.
Prism. Oh, that's good. Okay.
Yeah. So you have
rectangular
you have
prism.
shape. You have resolution that is coming from your mesh. And you have
Okay.
some total volume, like whatever
Yeah.
it is. So this defines your design space. This is
Mhm.
your design space.
Yes.
Now going back to this shape that we had,
Mm-hmm.
what we have also is some objective. What is our objective?
Mm-hmm.
Well, this is going to be depending on the governing equations. What is the physics you want to optimize for?
What do you mean?
It could be any physics. It could be aerodynamics. It could be linear elasticity. It could be
Okay.
anything. Okay.
Or you can, similar to your curve thing, somebody say, I want a shape like this, can you make it like that?
Sure.
Okay.
There's some governing equations
Mm-hmm. Okay.
to whatever it is you're trying to solve,
Mm-hmm.
and that comes with fundamental physics properties.
Mm-hmm.
So in this paper, what we looked at was structures. So minimum compliance, linear elasticity. I apply a force, things deform.
Okay.
Right.
Minimum elasticity, what does that mean?
Minimum compliance.
Minimum compliance.
Compliance is basically how stiff. So if I apply force, a specific kind of force to a structure,
How good you
how
fall off.
stiff it is.
Oh, okay.
Yeah. So objective types, so it could be stress. I want to minimize stress. I want to
Mhm.
minimize compliance,
Mhm.
overall stiffness, whatever. You come up, you'll pick your objective based on fundamental physics properties.
And this is the finite element that says every.
Finite element solves the equation for you.
Oh, okay.
Yeah. And you have some boundary conditions. That,
Oh, so those minimal compliance, those comes from physics.
Yeah.
Okay.
So your fundamental equations, your governing equations come from physics.
Mm-hmm. Okay. Okay.
Newtonian physics.
All right.
And at the end you have like how much
About
material.
tension, how they work, materials.
Yeah. So like
Alright.
Young's modulus, Poisson ratio, which
Yeah.
describes how
Okay.
a material deforms when you apply
I
force.
see. Okay. I don't know them because I'm not mechanical, but okay.
Yeah. So total material use is like how much material in this space do I want to use?
Mm-hmm.
That's your constraint,
Mm-hmm.
right? And then,
Oh wait, how much material I want to use? That's my thing. Are you gonna like stretch the thing, or you wanna add something from outside to it?
so you have some boundary conditions.
Oh, good.
You say, okay, this part of the space is fixed. Like I
Mhm.
have a nail here.
Mm-hmm.
I've nailed this to
Mm-hmm. It's just like
like
that.
yeah, something that's stopping motion here.
Like for example, this side.
Yeah, let's say like one side of this is like fixed,
Okay.
and I'm applying a force here.
Mhm.
These are my boundary.
What are the
conditions.
things? Yeah. What are the pokes you can do to this?
You can fix any point in space. You can
Uh-huh.
apply any load anywhere.
Applied load.
But
Like
force.
add mass. Oh, okay.
Apply
Okay.
some force.
First. Okay.
And
okay.
then you have like some amount of material you want.
And
to
you can
use.
cut, and you can.
Well, you can apply any kind of like you apply a force, a moment, a shear thing. You know, like
Okay,
all of
okay,
this.
okay.
Yeah.
What about mass? You can add material to it or not?
So this is the thing. You have this space, and you want to use a specific amount of material,
Okay.
but you want it within this space with these boundary conditions.
This is a space or this is the material?
No, this is the space in which we want to put material in.
Oh, so it's just empty space.
Yeah, this is just empty space.
Because it's silver, I thought it's like a piece of iron.
Yeah, but if empty space is just nothing, right? It's what we want. How do you visualize?
Yeah, okay, I got it. So, but we have a room, for example, and we wanna set the decoration inside.
Mhm.
Okay, go ahead.
And then based on this, you run optimization.
Okay, but these are material.
Yeah, so this is the thing figuring out where to
Is
put
it like
material.
3D printing?
Yeah, this is you can 3D print this, for example.
So this the application is for 3D printing.
Application is to like given a specific problem, find me the stiffest possible structure. And then I'll go figure out how to manufacture this.
This is a stiff structure, actually.
This is for the specific boundary conditions that were given.
Oh,
This is
okay.
the stiffest possible structure.
It looks very fragile.
because the total material use that we allow is very little.
Okay.
So-
What was the application for this?
You want to see some of the real things.
Why does it have so many holes on it?
Because well, you want to use less material.
Dude, that's crazy. Do you use LLM for this?
Not LLMs, generative models, but not
Uh-huh.
LLMs. But like topology optimization,
Bruh, that's the crazy
like
thing.
bike frames. Like if you look at some of those images, like
How
these-
many people?
these shapes, they're not very
Okay.
natural, right? Like, they
Yes.
look like bones, basically.
Exactly.
Yeah, so
Very light.
nature
bruh.
did topology optimization through evolution.
All the what are birds are like this.
Yeah,
Their
they
bone
have hollow
structure.
bones, yeah, like or like a bike like this. Like these shapes appear
What is the
when you
thing-
optimize.
material they use usually? Carbon.
Carbon fiber.
Carbon fiber, right?
Yeah. So these things, these kind of weird shapes.
How much is this bike?
I don't know.
All right.
Yeah, these kinds of weird shapes and stuff that appear in nature a lot of times.
Yes.
If you wrote down the physics and tried to optimize for it, you kind of see them happen.
Yes, it looks like a bird's bone actually.
Yeah, so it looks like kind of like a bony thing.
And all of these we can do just in the past 20 years.
Yeah,
Like-
because they say, yeah, exactly. I mean, numerical methods before computers were like people did have numerical stuff.
Mm.
They had to do it by hand.
Yes.
Couldn't do it at this kind of resolution and stuff. Right?
Yes. This is something only from machine learning.
Not machine learning. No. You can run conventional optimization on this.
Okay.
Yeah,
Okay. It gives you this form.
Yeah.
Oh shit.
Actual, yeah. If you run the physics optimization, this is what you
Okay.
Right. So what was novel about this is before we did
Shit. What are those governing equations that end up? with
very.
it?
By the way, it's very simple. The
Right?
governing equation is super simple.
Governing equations are simple, but the solutions are very not natural.
Well, actually, if you look at nature, you see them in like bones.
You
and
need to
stuff.
kill a bird first and then.
Yeah. If you look at linear elasticity
Well,
equations.
our bones do not have.
There you
this
go.
kind of-
This is it. This is your system of partial. This is your partial differential
Oh,
equation.
shit, okay.
Linear.
Linear.
Linear, super simple. Yeah.
What about our bones? Is it also when you look at them, they have like holes and stuff? Or
Bones are actually so they have they're like more metamaterials than they are.
Minute
They're porous
material?
metamaterials.
Metamaterial.
Yeah, metamaterials. They're like porous material.
What
They're
is
full of
metamaterial first?
Metamaterial, it means you come up with a tiny unit cell. That is what they call a unit cell.
Mm-hmm.
It's just like a little cube
Mm-hmm.
where material is positioned in there somehow. Like
Mhm.
the same thing as topology optimization, but it's a little cube.
Okay.
And then you put all these cubes together to make the whole thing.
Okay.
Like let's say I have this shape.
Like, is it like graphite that we have this hexagon shape and then we put a lot of them next to
Yeah,
each other?
yeah, exactly. That's your unit cell. This is
Ah,
the
okay,
unit,
okay,
and you put them
okay.
together. So like, if you look at
But they are all from the same elements, but they have this
they're just it's the shape.
network structure
like
to
this.
them. All right.
It's a repeatable unit cell. You put them together. Like
okay,
this.
okay, got it.
Like that's
Is
the
it
metamaterial.
material, really, or it's just a model?
You can print it out of any material,
Okay.
but like it looks like this.
It's real. All right.
These are real. You can make them. Yeah, linear analysis is a very simple equation, right?
All right.
There's nothing,
Yes.
nothing complicated about this.
Wow.
But the outcome is that.
That comes that.
Yeah, because
So, but they have the building blocks.
for metamaterials,
Yes.
you find the building block's shape using this.
Yeah. Okay.
You
So
find-
now it makes sense why. But the shape you showed us, it has like very like the holes are not similar to each other.
No, they're not. No, this is imagine this is the whole unit cell.
Oh, this is a unit, and then this
This
will
is
be,
the whole problem. No, so if
This will be
metamaterials.
repeated, or no?
No, this is not a metamaterial. This is like one problem, like the bike frame.
All right.
The bike frame I showed you.
Uh-huh.
I would say so. Okay, I say my bike wheels are here, so my space is like
Tesla
this.
should use this.
They do.
Instead of their stupid truck.
They do this in aerospace. They do this. It's very
Ah.
expensive to make these. That's the problem.
Yes.
The-
Who wants to create
The
them?
the manufacturing of a shape like this is very hard.
3D printing.
Yeah, but the 3D printing has like very specific outcomes. Like okay, it's a polymer first of all. Usually,
Yeah.
it's not metal. It's like there's a lot of things to consider.
What are they doing for creating this stuff?
There's different ways they manufacture them. You can actually make metals. Like in aerospace, they have ways of making these out of metal
Uh huh.
by like sintering or 3D printing metal, or like there's a complicated plasma manufacturing
That's
method.
crazy. I think there is a lot of room
Okay.
here.
Yeah, so manufacturing these is actually kind of easier than the semiconductors. Because
Oh.
the semiconductors, you're like almost at atom level.
I don't know. They like you remember in my electronic courses. They were okay. We got so small. Where are we going?
Yeah, it's like right now it's like 3 nanometers.
Yes,
Like
yeah.
3 nanometers is, there's a few atoms. You're
Yeah.
laying a few atoms.
Exactly.
Yeah, so people figure out how to make weird shit.
This is crazy, right? Okay.
Anyways, so what we were like proposing to do was okay, existing works in literature on topology optimization using deep learning.
Mm-hmm.
They can't handle 3D, first of all,
Mm-hmm.
but like the real world is 3D. You're not optimizing 2D shapes.
Wait, what can't they do 3D?
3D shapes.
They cannot do 3D shapes?
No.
What do you mean they cannot do 3D shapes?
They do 2D
Who?
topology optimization. The existing works.
Oh, okay.
Yeah, they don't go into 3D very often. Yeah. The other thing they can't do
And
is
you did it in.
yeah. The other thing they can't do is different resolutions, like different shapes. What if my domain shape changes? All the models that are out there, they just do a cube. They always use a cube.
Oh, you're saying prismatic.
Yeah, I'm saying like whatever shape you give me. I want to handle any kind of shape. And because this is like
So the shape is just your boundary condition.
not boundary condition. The shape is your domain shape.
All right.
Like if you integrate over what? Integrate over like this omega space. This omega space has a shape.
Okay, now I like this one more actually compared to your first slide, because now you can see that this is your space that you can work in, right? And this material is inside this space.
Yes.
All right. But this one is out of it.
And that's just animation. It's
Oh,
kind of
that's just
broken.
animation.
Yeah.
Is it also Adobe?
No, these are I rendered these manually in Python.
Wow, dude, they take a lot of time.
Yeah, it takes a bunch of time to make visualizations, but I think it's worth it because it makes the communication more effective.
Definitely it does, but
Yeah.
like I am plotting two curves next to each other in Python. It takes me.
Yeah, I mean at this point I've done so much of this that it's not so hard to do.
All right. These are cute, by the way.
Yeah.
So what
resolution-free domain adaptive, meaning any resolution you give me, any domain.
Oh, okay. You said that the people have done topology stuff on the say 2D, but
2D
3D?
with deep learning, they've done it with 2D.
All right.
And I want to so this is like our work, right? We made this generative model that comes up with these topologies
I
on
see.
on the fly like this. And I want to compare them, how fast they are to if you use the conventional optimization.
Okay.
Conventional optimization meaning you use the gradients.
Yeah.
How you get the gradients and stuff is like you gotta find the adjoint. Who cares?
Mm-hmm.
You write those equations down, whatever. You figure it out. It's not that bad. This is the conventional optimizer. We're done. This is our model. It's done.
Oh, it's already done.
Yeah. Conventional optimizers are still running. It's still running.
But they look similar, right? But
Yeah, because they have to. Optimal is optimal, right?
I mean, you in your previous work, your accuracy was higher. Here, it's
No,
just
here it's gonna
a
match.
matter of time.
It's simple.
Well, the second parts are a bit different.
Yeah, it's slightly different.
Yeah.
The deep learning model is again not precise.
Oh, okay.
Like, you always have that caveat.
So you come with this, and then you'd run an optimization.
very few steps of it because I
Okay.
don't need to run as much.
Okay.
The optimizer has to go from nothing.
Mm-hmm.
Right. The goal here is to
Oh,
speed
these
things
ones
up.
are also a bit.
Yeah. The goal is like we are 15 times faster if we use deep learning.
Should I run it again to see 15 times?
Well, this is actually sped up.
wait.
The optimizer. We'll get to the speed up. You'll see.
Oh,
the
how
speed
long
up
does
later.
it take in real?
Our model takes about 16 seconds.
Okay, that's not bad.
Yeah. The optimizer takes. If you run on CPU, it takes like 30 minutes for each problem. If you run it on GPU,
That's actually short too. Like, okay.
yeah. If you run it on a GPU, though, it takes like 6 minutes on the optimizer.
All right. So, wait a second. 6 minutes is enough. Why did you improve it?
Yeah. Okay. This is like you were literally going slide by slide, right?
All right.
Topology optimization is a platform for proof of concept. It's
As
not the
in-
specific problem that I want to solve. It has some properties that
Wait,
make it
knowledge
useful.
organization, a platform for proof of what is proof of concept? POC.
Yeah, it's like this is not a thing that you would apply in the real world, but it demonstrates what is possible, right? Like the point is not
Like
to,
kind of reasoning why we should do that.
yeah, why we should do it, and like why it doesn't matter.
Mm-hmm.
So first thing is complex physics, right? You got these like weird PDEs. It can be aerodynamics, it can be heat, it can be
Oh,
linear
this is
elasticity.
All right.
Yeah.
What is this third one?
It's just stress field. This is just a stress field.
Is it a bone?
No, this is just a beam. The load is applied. This is how the stress gets.
Ah, okay,
Propagated
okay,
there.
okay.
Anyways, and it's a complex optimization problem, right?
What is a complex optimization problem?
Well, what I mean by that is it's non-linear.
Mm-hmm.
It is non-convex,
Mm-hmm.
and it involves different types of constraints. So why do
What do
I
you mean different types of constraints?
inequality, equality, and also non-linear, linear? Your
Okay.
constraints are anything.
So I think the non-concave part, convex part.
That's the main thing.
main thing. Okay.
Anyways, the point is you can't actually run optimization
Mhm.
on aerodynamics because it's too complicated and it's not differentiable a lot of times. Even in these,
Aerodynamic. This one.
yeah,
You cannot run it because.
it's not a differentiable. There's no adjoint for it, and actually calculating numerically calculating the gradient is impossible. It's just too much.
Wait.
The other problems, okay, the simpler problem.
Mm.
Linear elasticity, we can run it, right? We saw that you can have
Linear elasticity is this one.
is the ones we've seen so far.
Okay.
Yeah, it's like these
That you
problems.
pressure something.
Yeah, these problems.
I don't know what they are actually.
Yeah, we'll get to that
Okay.
later. But yeah, like for example, this one we ran it on linear elasticity.
Dude, by the way, they can be nice pieces of art.
Yeah, you can 3D print them just because they look cool.
They look cool, really, like it's like, as a decoration at your place.
Yeah.
What was that? You know Steven, right?
Yeah.
Kinematic Cinetics. He had like a artwork thing. He used to post a lot of stories about that. Like
He was in robotics, right?
he was in Media Lab Robotics.
Yeah.
I think those shapes were different, but they were also crazy. They look beautiful.
If you optimize for different kinds of things, you get
Mm.
different kinds of shapes.
I see.
Like I can show you what like if you optimize for heat conduction, what that looks like.
He named it Kinematic Cinetics.
Synthetics or
Synthetics. Yeah.
topology optimization heat transfer. If you look at the images that those generate,
These are crazy.
yeah, like these shapes, like
Kind of looks like fractal too.
yeah, they are kind of like fractals. Yeah, so this is like to get the maximum possible heat exchange.
Ah, because you want to have the
Yeah, like
surface.
Yes, in 2D they kind of look like this.
Oh shit! This is fractal. I think the optimal solution.
Kind of like
yeah.
is kind of like a fractal.
I see.
This is like not a convex problem, so it's not like this is one.
Wow,
solution.
dude! If somebody explained when I was 18, explained like mechanical engineering like this to me, I would have changed to like, okay, we need a good computer scientist to show and come and talk about
I
their
think
work
so.
too.
These kinds of things, it's computational work.
Uh-huh.
So it is computer science plus. You know,
Yeah,
mechanical.
you are also doing a lot
Yeah,
of
that's
machine
what I
learning.
do, yeah.
Now, by the way, everything
Everybody's doing machine learning.
machine learning. So you need to know everything,
Yeah.
kind of.
So this is a complex optimization problem. It's also like arbitrary design space. It can be any shape,
Mm-hmm.
which is good because in precision engineering you never know what shape. Like if you're trying to optimize the material distribution of a wrench, the shape
Wrench?
of a wrench.
What is there? Oh,
So-
this. Okay.
You don't always
What
get
is ratchet, by the way?
a ratchet is like those things that make it click click click.
So why do you say the airplane was ratchet?
Oh, that's just it's an
That's
expression.
a slang.
Yeah, it's just like
Oh, okay.
it's like
All
bet.
Huh?
It's like bet.
Bed.
So they say,
Words.
you tell me.
No cap.
Yeah, no cap.
I
Yeah.
see. Okay.
Anyways, so and also we have strong baselines for certain kinds of problems. As I said, like not all physics you can do this with. You can't run conventional optimization on any kind of physical problem.
Like the air
Or if you mix physics, like if you mix heat and elasticity, you want it to be stiff, and you want maximum heat transfer. You have multiple physics,
multiple governing.
you have
equations.
multiple governing equations, or a mixture of governing equations. You most of the time you won't be able to run conventional optimization.
Why? Because it gets not concave.
No, because you can't differentiate, or it's too expensive to differentiate it, or like get the derivative, get the gradients.
So for this one, for example, for the middle one,
You can. This
is for heat.
heat equation is Poisson equation. You know Poisson differential equation?
I guess I know. I remember.
Simplest possible
UT
differential
equals
equation.
something. UTTT CCC.
Yes.
Okay.
It's the simplest possible differential equation you can have.
Alright.
That's heat.
Mm-hmm.
Right.
Well, we have this in Riyazi Muhandisi, mathematical engineers.
Engineering mathematics.
Engineering
Or
mathematics.
engineering calculus.
All right.
We also have
A lot
strong
of bad
baselines.
memories.
We also have strong baselines.
So wait a second. You say once we mix heat with
Elasticity.
elasticity, it fucks up the system.
Yeah,
Why?
it becomes so you can't find the adjoint. Well, in that case, you can actually. You can use optimization. It's not a good example, but aerodynamics plus heat, aerodynamics plus.
It becomes too many, and then.
No. Okay, so to solve these, you need the gradients. The gradients are not always practical to calculate numerically.
Oh, okay. So.
If you can find an adjoint, it's kind of like a closed form thing.
Mhm.
Not really. It's like, can I solve one system of linear equations to find my gradients, or do I have to run, like if I have n elements, do you have to solve n different equations that numerically find
For
the-
each one.
Yeah. The point is sometimes you can write the adjoint,
Mhm.
so you just solve one system, you find all the gradients,
Mhm.
then you can run optimization. If you can't, You have a million elements. What are you gonna do? Like every step of you need 500 steps of optimization. Every step involves
so it is
a million simulations. That's you can't never. You're never gonna do that.
Adding too many physical governing equations.
It makes it so that you don't have like a closed form thing to solve. Right. Yeah.
Okay, makes sense.
Yeah.
All right.
So, but we have strong baselines for simple problems.
Mm-hmm.
So if you develop methods, we can test against optimizers that find very good solutions.
I see. Okay.
So that makes it like a good platform for us to like develop the foundation models for complex engineering design problems.
Okay.
Like if you have different kinds of engineering design problems where you want to do optimization for, what if we don't have optimizers? Like that, the linkage thing is like that, right?
We don't have the optimization.
We do, but like it's insane. Like the combinatorial thing is just nuts.
Yes.
Goal is like this is why we do it on topology optimization because.
Dude, how many citations your work got for this?
This is just published. This is like 2
what about
citations. That one is also recently released. So none of those.
Isn't there any proof?
The older ones.
Isn't there any proof of concept that it gets like thousands of citations in a year?
No, not a thousands of citations. I mean, not a mechanical engineering.
You
don't have that kind of volume.
What is the impact factor, you think? If there is 1 to 5? I feel this is a really nice
For which
one.
ones?
The presentation at least was nice.
Yeah, the presentation.
Well, I don't know mechanical engineering, so I don't.
Yeah, no, I don't think they're necessarily like individually super impactful.
Mm-hmm.
I think it's like a body of work. You got to look at it like as it develops.
Mm-hmm.
And mechanical engineering moves slow because of there's some very traditional academic things.
Okay.
But I think some of they've been highly cited considering mechanical engineering, the works that I have done.
Mm.
I have like 400 citations.
What was the feedbacks from the retrieval? That was groundbreaking. What was
which ones?
Like you submitted.
So when I presented this in the conference, people were impressed.
Impressed.
Yes.
I see.
But not like, oh my god, my mind is blown.
Standing ovation.
Yeah, like, not like that. It's not like a Nobel Prize or something. No, it's like they were like, oh, this is nice. Like this is a step forward because we didn't do 3D before, for example. Right?
Oh yeah, that's a big thing.
Like we didn't do arbitrary shapes before.
Yes.
We didn't. So these are new things you did that are, if we are ever going to get there in using AI in solving these problems, we need all of these things.
All right.
Right? So these are like a step forward.
What was the...
And it's a conference paper. It's not even a journal paper. This is like a small work.
Okay.
Like this is considered relatively like small.
What about the other one? What about the...
No, that one is a bigger work.
And what was the impression?
Reviews were good, but that was not presented anywhere.
Oh, you did?
So just to say this, my advisor for his 10-year review, he has to have his like top 5 most important works that they submit.
Oh, it was one of them?
Yeah, he submitted this as one of them, and also
he didn't do anything about it.
Yeah, but that's kind of the point of the PI. Doesn't really do the research, but he also has to present like a seminar thing. The way it works in McHugh for 10 years, they present their most important works.
Okay.
But you have only an hour, so you really usually
jump.
You mention 5, but you go into details on 2, and this is one of the 2 that he wants to present. Yeah.
Okay.
So the linkage thing is we've been working on that for a while.
Fadil, who was
Faiz.
Faiz, you have your 10-year because of Amin.
No, I mean
half of it.
He got a lot of money into it, like all the grants and stuff that he's wrote.
Okay.
Yeah,
that's actually the thing.
That's a more important thing.
More important thing, right?
Yeah, it's probably the most important thing. It's how much money you get in. Yeah.
How many works he has done onto his 10-year that he decided to choose this one?
I mean, there's a lot of papers. If you're just counting papers, like probably 30 papers, 20, well, actually more. 40
Which
papers.
one of your papers you are the most proud of?
I think that's the linkage one for now, but there's more coming.
More coming.
Yeah, the good ones that are at the end of PhD.
Okay.
Yeah. The actual good ones.
All right.
But so far, it's been all partial works. Anyways, I don't want to go.
Dude, your slides look so good. Dude, you put energy into this stuff. How long?
These are prior works, so I'm just going to. Yeah, I don't want to go through this.
Okay.
Because I think it's like less important here.
Wait a second, I lost the track. Where were we? 3Ds? Oh.
Yeah, we were talking about like the limitations of the current AI, but like we talked about why topology optimization or like minimum compliance topology optimization is like a good place for us to develop proof of concept.
Proof of concept.
Yeah. Yeah, but here I'm just going over the limitations of current works and why they're limited to specific domain shapes, resolutions, and they're not scalable to 3Ds because they use convolutional networks. the way they represent boundary conditions.
CNN convolution or CNN is a
News network.
no, it's not that convolutional
Yeah,
neural network.
convolutional neural networks.
All right.
Yeah. So the issue is how they present boundary conditions is also a problem they have. They use limited data.
Oh wait, so for this work you didn't use CNN, you came
No.
up with another
Yeah,
technology.
we tried to do something that is generalizable to different resolutions and shapes and so on.
Okay.
And then often they don't have precision, which is the IBM thing.
Mm-hmm.
The IBM could work.
The on the left one,
Yeah.
I guess. Okay.
So we did our model, which is resolution domain shape. It does not utilize field.
NTO is
NITO, that's the name of it.
NITO.
It's the name of it's neural implicit topology optimization.
Implicit. Why is it implicit?
Implicit because I'll get to why it's implicit because you get coordinates in and you get a field out.
You get a coordinate and?
It's a function of coordinates.
Mm-hmm.
You train a neural network that's a function of coordinates x, y,
Mm-hmm.
and that's in literature that's referred to as an implicit neural network.
Okay.
Yeah.
And neural is because they're like
Neural
letters,
networks, yeah.
right?
And then whatever we come up with a new data set that's larger than existing ones, and then we implement a few steps of direct optimization as a mechanism.
Is there any part of this like you have experimental results?
Yeah.
Like on physical objects?
No, just simulation.
Simulation.
Everything is computational. Yeah, everything is computational.
Simulation. All right. Okay.
So this is our method. The basic thing is you have some boundary conditions in space. In literature,
Wait,
usually
what is this? Fixed in x, fixed in y,
fixed in z.
What is fixed in y? Oh, these
These
triangles,
points,
these
the-
points. Oh, these are the boundary
Yeah,
conditions.
these are boundary, and then you have some force applied.
Where are the force applied?
Yeah, there's one force
Red.
applied.
Okay. So you say if I have a bar and fix it at these 2 points and put a force here, what
Here,
happens?
what-
Oh, what will be the tension?
What would be the stress or the
Stress.
shear, whatever?
All right.
Yeah, so
Inside.
usually in
In
literature,
a molecular level.
to the material,
Okay.
not molecular level,
I know. Like
Newtonian, so like-
Newtonian, continuous.
continuous.
All right.
yeah. So the field so people use fields to
Mhm.
represent these boundary conditions. They don't input. How do you input this to a neural network? You really can't.
Okay, what is field? By field you
So
mean
you get
vectors?
stress. So so what they do is they say assume there's material everywhere,
Mm-hmm.
simulate this, calculate the stress everywhere, and
Mhm.
use this as a representation of the boundary condition.
What is this?
This is the stress field.
When you say field, what is field?
Like the orange is high stress, blue is low stress, or the other way.
Ah, okay. I mean, what do you mean field? Like it is
Field is the function of x, y, z.
level sets, kind of level set demonstration.
Well, that was but like it's a continuous function in space. That's field.
Oh, continuous. Oh, I thought in.
It's a continuous scalar in space. Like it's a function of x, y, z, and then you can move in the direction of it or whatever. Like gravity.
A function from R3 to R.
Yeah, it's gravity, like for example.
All
It's a
right.
field, yeah, and this is a stress field, basically saying, oh,
You want
what is
water?
the stress? No, thank you. What is the stress in different parts of space?
How long is it? Has it been? Just a second.
It's been a very long time.
It's been like that.
3 hours probably. So we talked about so much shit.
Dude, we didn't drink any water. Where is it? 2.5.
2.5, yeah.
All right. Go ahead, sir.
Yeah, anyways. Yeah, so usually people use these fields. So because this is hard to input to a neural network, they use these fields. So you can think of this as an image.
Well, you need to solve the field first, right?
Yeah, you can solve it with
Easily.
finite element quick. Yeah.
Okay, okay.
Yeah, so they input this. It's like an image almost.
And this is like this purple point
Is where the force
forces
applied.
and like
So there's high stress there.
and probably
And
these
this
are
is the fixed point, so there's high stress
orange
there.
is less because they are free.
Yeah, there's nothing there.
Nothing there. But this sticking point is not
You can
very.
see behind, so you can't see it, but this you can see.
But you're saying that one is also more purple.
Probably high
I
stress
see.
as well.
Okay.
Depending on the direction of the load, actually. If the load
Okay.
was purely in this direction, there'd probably be very little shear there.
Uh huh.
Yeah, anyways. So they use this as a representation.
Oh, and these dots are like fixed in X, fixed in Y,
And Z.
Sometimes they can rotate. If
Sometimes they're only fixed in X, for example.
I see. Okay.
For example, you have a roller.
roller is fixed in X and Y.
Yeah, for example.
But if it is fixed in X, what does that mean?
Only in X.
Yeah.
Okay, imagine you have a little like piston somewhere
It can
and
go
it's attached only, so
forward.
it can so it's fixed in two directions, but it can move in only X. If it's only fixed in X, then you can think of it as you can move it on in Y and Z. So you
In
can,
a page,
you put
right?
like a little roller thing here,
Uh-huh.
right? So you can move in X and Y, but you
Uh-huh.
can't move in Z.
Okay,
Yeah.
okay.
That's why I represent them with
Mm.
these like weird little balls.
Mm.
Yeah.
Okay.
Yeah. This is what people use. But the thing is, this is going to have a specific resolution and shape
Mhm.
based on your domain.
Yeah.
If your CNNs are not able to handle different resolutions and shapes, you use these
Okay.
fields, you're kind of shit out of luck. You know.
Well, they don't take it as an input, right?
No, but so this is hard to input to these models, but we say, okay, no, there's a way we can input them.
Okay.
We say, all right, we'll use them as they are, like raw.
Mm-hmm.
Okay, there's a specific position in space that is fixed. There's a position in space that is load applied. We'll represent this as a point cloud,
Mm-hmm.
which has X, Y, Z, which is its position, and then
All of them?
so X, Y, Z. If it's 0, it means it's not fixed.
Ah,
If
okay.
it is 1, then it means it's fixed. So it means
Isn't
like,
it like ChatGPT that they say they put the translation of a sentence, like two languages, put the sentence and its translation next to each other? No, that's bullshit.
it's guys, but yeah, this is just one way to represent these. That is
Ah,
general.
Okay.
You can have different number of boundary conditions,
Yeah.
whatever. It will still be like this.
Yeah.
This is the closest real representation of the
Alright.
problem, right?
Sorry, in the name of it, field
Point cloud.
point cloud representation, which means you are
It's
embedding
cloud.
them in a like a more sixth dimension, and then,
Yeah.
Alright,
Yeah.
go ahead.
And then, so the way you need to input this is we come up with a way to input arbitrary numbers of them.
What is this graph? So you have
It shows
this.
what the architecture. Yeah, so you have this as your problem
Domain
definition. There's a domain shape. There's a target volume fraction,
Of course, alright.
and you have some
Target volume.
how much
for-
material you want to use.
Okay, why
What
do you
fraction of
why
this
do you,
do you want? This just because it's the terminology used. In
Oh, volume is the volume, okay.
Yeah.
Fraction is the fraction of the space.
Yeah.
Alright. And then you're forcing here, you want to come up with a design, like the putting this material in this space,
Yeah.
this cube, that is the most, for example, stiff against this force, and these points of those materials should
Yeah,
be.
this is your boundary condition, whatever that may be.
I see.
So we come up with these models. We call them BPOM. They can handle arbitrary numbers of boundary
So
conditions.
method, we use a boundary point
Order
in
invariant MLP.
BPOM. Alright, they already once you
This is
have
what we
a
come
wo-
up with.
Once you have a word that has another abbreviated word inside it, it means that you went too far.
Yeah,
Alright.
it's what can I do?
Yeah.
Whatever. The idea is you can have any number of these points because
Uh-huh.
we're not limiting our problem to anything, but we still want a fixed length representation.
Dude, to
And
be
this has to be order invariant.
so you got
I don't
a-
care about the order of the boundary conditions. I just care where they are.
That's true.
So we want order invariant, and we want to handle any number of points.
Any number of points.
Yeah.
Yes, okay.
So we do what
You
I
can
want.
also have boundary constraint the whole page, right? Like the
yeah,
whole
yeah, you can
plane,
have
the whole
plane.
side.
You can
Alright,
have like
alright.
many.
Yeah, okay.
Yeah. Anyway, but this is generalizable, basically. This
Uh-huh.
idea is like you get a latent constraint representation, which is fixed length,
Mm-hmm.
and it can represent any problem.
You mix all of this data to this.
Yeah, and these are all learnable things.
What
These are
is
models
FC layer?
fully connected layer.
That's something about machine learning,
Yeah,
right?
it's just an architecture thing. It's a
Okay.
yeah.
BPOM is not
It's
like
the model that we came up with. It's in the paper. I mean, for
So
a
you-
presentation, it doesn't really matter what it looks like architecture-wise.
that. Yeah.
It's an architecture that you can
So
train.
wait a second. You give these points to BPOM. What it gives you this
It's a
same.
fixed length vector that represents
So
the
it-
boundary condition.
like what is this two square? Like what is this? Oh, they are
It's a dot,
dots.
dot, dot, yeah.
Dot. Okay, okay.
It
So you take 6 elements and
can be
then
many forces. I don't know how many.
okay,
And I always give you the same length
same
vector.
length.
Yeah. Doesn't matter how many you give me. I
Okay.
always give you the same length.
It's like large language models because they
Yeah.
also take same and
Yeah, like you
square.
take any the length of thing in there, but it will always give you the
The
one.
name number of tokens
Yeah.
are the same.
Yeah, so it's kind of like that, but for points in space.
Why they are BPOM but this one is
Because this is just like a single values, continuous value. So it doesn't need. It's not a point cloud. So fully connected layer is the simplest thing. It's a multi-layer perceptron. It's like single layer perceptron. It's like matrix multiplication.
matrix multiplication. And the input to it is the volume and
It's a 1 by 1, and a matrix is a like n by 1 that you multiply to. I just
What
want to increase the dimensionality of it. That's it. And the weights of that matrix are learnable.
Okay.
So you train the weights of the matrix.
I didn't get it. What are the inputs to this?
Just a single number.
What is that number?
The amount of material I'm going to use.
Okay. But also we got this arrow here.
Yeah, so both of them go to FC layers. Domain shape is the shape of your domain.
Which is not one number.
No, it's 3 numbers. For rectangular prisms.
Oh, for
X, Y, Z.
rectangle.
Yeah. Here it's demonstration only. As I said, this is like early work.
I see.
Yeah.
Is it like domain shape usually just what are-
Arbitrary.
arbitrary?
It could be represented with CAD, it could be represented with whatever.
Oh, okay.
Yeah, so the shape. Okay, the point is there's already machine learning models
Mhm.
to handle embedding shapes into a fixed like vector. So
okay.
I just want to demonstrate that we can make an architecture that can learn this. That's all I want to represent. Here I want to say that it's possible to do this
Mhm.
with machine learning, and it is a way faster than using optimization.
Okay.
Because the point is to demonstrate that you can actually do it,
Mhm.
because people haven't really done it
Mhm.
properly like this.
So this is why we call it proof of concept.
Yeah, that's why we call it proof of concept, because this is not something you
Right.
use, right?
Yeah.
Like this.
Why don't we use it? Oh, we haven't built the.
I mean, the optimizer exists. Yes, it takes like 30 minutes or whatever, but I mean, if this was robust and
Mhm.
fully done and finished product, there's startups that are
Okay.
doing this kind of work. There's like
Uh-huh.
not one or two. There's like I know like 20 startups that are doing topology optimization.
Ah, okay. What happened to your startup?
I'm working on it.
Working on it.
Yeah.
Alright.
And this is the architecture of the actual implicit model. So the implicit neural field takes that latent constraint representation that we came up with.
Dude, I'm fainting to be honest. I need some. Okay, I have some rich stack. Let's go get some of them. Pause it here.
I mean, I can finish real quick.
We can finish it.
Yeah, there's not much left.
Dude, I want to learn it because I feel the last 2 slides I am losing my efficiency. I did pretty good. I'm following up. I think it's very also intuitive.
Yeah, these are very okay. So machine learning literature, in my opinion, because it's so empirical,
Mm.
there's not much theory.
Yes,
It's easy to understand.
dude, there was no theory.
Yeah,
That was really good actually.
there's not much theory here. I mean, yeah,
I
sure.
couldn't. I'm imagining, for example, me doing my paper to another person.
Yeah, your work is very hard to. So I have
I'm
to take
getting-
a lot. I have to take a notebook with me and start
Yeah.
writing notes. And
Is
follow with
it
you.
my presentation that sucks or is it
No, I mean the nature of your work is like that, but your presentation.
sucks?
No, not that it sucks, but it's like you could keep it very high level,
Yeah.
but then it depends on your audience. If your
Exactly.
audience are already like game theory, mechanism design people,
Mm-hmm.
well then they all understand most of those equations.
Yeah.
You can go through it real quick.
Yes.
But if it's just anybody, then you may want to keep it high level.
Yes, I want to keep it.
You want to keep it like visual mostly.
Yeah, visual.
Just like, keep it visual. Put like small amounts of stuff on your slide and explain it.
No,
Like,
I really.
You're there because your
definitely,
slides.
you put a lot of energy into your slides, but like you have a lot of graphs, shapes. All of this takes a lot of energy for me, but it gives me like these big pictures that I can relate to.
Yeah, it's
What is Mesh doing in this project?
it's the meshes. Is the
Okay,
meshes.
I mean, give me like 5-minute break.
Yeah.
We will come back and finish it. All right.
Okay.
So let me pause this because we don't want to go for a second video.
Yeah. No editing.
Consistency. Nothing happened.
Yeah. No. I didn't time it at all.
Okay. We were here all the time.
Yeah.
All right, we are back.
So I think we'll see you
Okay.
Yeah. So yeah, we had this latent constraint representation.
Mm-hmm.
We had like all of our problem definition and constraints and so on in there.
Uh-huh. What did you send me? Oh, to the professors. Right. Okay.
Yeah. So the idea is
We embedded all of them with BPOM into this space, and where does this weird shape coming from?
yeah. So this is coming from this. So this is like an implicit neural network, meaning as input you give x, y, z coordinates, and as output you get some field value. In this case, would be density.
So it is a density. C is the
The constraint representation.
constraint.
The
Theta is.
the parameters of the model.
What are the parameters of the model?
The weights in the neural network. VPOM, all those stuff. They're all trainable variables.
Oh, okay.
Yeah.
And X is. Oh, okay. Rho.
X is the coordinate, X, Y, Z.
And rho hat is the density of the
Density.
material.
Yeah. Or you can think of it as probability of material existing in that
Okay.
coordinate.
Okay.
Like the
Okay.
probability of material existing in that
Yeah.
point.
Wait, it's 1-0, right?
In reality, you don't have like half
yeah.
a material.
Yeah. Right. Okay.
So it's a binary thing, but
Mhm.
yeah. Anyway, so the way it works is you give as input some coordinates,
Mm-hmm.
and then you have like multiple layers of neural networks.
Mm-hmm.
The important thing is how do you send this information to your neural network? And the way we do that is through modulation of layer normalization, or a conditional layer normalization.
Okay.
And layer normalization is one way to normalize the outputs of a neural network layer. So the outputs of the neural network layer go in there,
Mm-hmm.
and they get normalized to a
So it's
0,
like
1.
a feedback system.
They get normalized to a 1,
No, it's
0.
not a feedback system. Here they are coming here, they are coming from below to the top. It is a feedback system.
No, this is not feedback. It just goes in.
Okay.
This only goes in.
Okay.
Yeah. And then layer normalization, what it does is it normalizes the outputs of each layer
Mm-hmm.
to the distribution, to a normal distribution.
Dude, die.
Well, not a normal distribution, but it normalizes it to a mean and standard deviation, mean of 0, standard deviation of 1. That's why I say layer norm 1, 0 here in this equation.
Mm-hmm.
And then what we do is we apply a sign like nonlinearity. The reason is in literature again, like this is the machine learning thing, right? Everything's empirical.
Okay.
People have found the sign activation function works well for
Works
capturing
well.
high frequency features.
Isn't crazy?
They do have some lemmas and some proofs of some things, but
I mean, like-
not rigorous. Anyways, it's
Alright.
mostly empirical.
All right.
So we just take that from literature.
Mm.
That's what we do. And then basically we apply some sort of modulation. So alpha and beta are basically also neural networks.
Mm-hmm.
They're trainable.
Mm-hmm.
They take as input this constraint representation and give us some scaling,
Mm-hmm.
which is like what standard deviation should it be, plus some um, shift. Which is what's the mean for each of the outputs should be, based on the condition. And we do this at every layer of the model. So every layer in the model, so we stack these layers. We stack multiple of these
Yeah.
layers.
Why do you need so many layers?
Again, this is just mostly like
Architecture.
more number of parameters means you probably can capture a larger data set.
I see. Okay.
Yeah.
Okay.
So LLMs, why do they have like 400 billion parameters or
Is
whatever?
it trillion for some?
No, it's probably still in the billions.
Okay.
But like hundreds of billions of parameters. Because the more you have, the more capacity you have.
Yes. Okay.
Yeah.
Makes sense.
Anyways, so at this point, like this is kind of what this does,
Mm-hmm.
and it gives us out as output some field, which is the density field.
Mm-hmm.
And at the end, what we say is that there's a lot of problems with generative models. Okay, here's some examples from a generative model's perspective. What a generative model is doing is it's learning the distribution of your data. It's learning your data distribution.
Mm-hmm.
So it learns to mimic your data set. So similarity is the main thing.
Mm-hmm.
Now,
Blind spots.
well, blind spots, but also if you look at all 4 of these images that I have here,
Mm-hmm.
they are visually similar.
Yeah, but
So from a statistical perspective, they're very similar.
Mm-hmm.
But if you look at the physics of the problem, having a gap here
Yes.
is a huge difference. So
Yeah.
compliance goes to 200 versus if you didn't have the gap, compliance is 66.
Mm-hmm.
Right. So generative models like the ones that we've talked about, they are
They are
susceptible
not.
to
They
this
are
issue.
not. A and B are different from C and D, right?
Yeah, A and B. This one is like it's like not zeros and ones. There's like smoothness.
Okay.
This one has a gap and it's smooth.
Uh,
And this one is like what you want actually out of your model.
okay. That C is the best.
Another issue is these 2 images, B and C here, are very similar.
B and C are the same B and C or different?
No, this is different. I'm
Okay.
talking about the figure below.
Okay.
B and C are very similar in visual. Like visually, they're
Yeah.
similar. However, if your load has even a slight angle,
What is the load?
So the load is, so you can see
Oh,
the
this is
problem
for
is-
this
yeah,
page.
yeah.
Okay, what is this story here?
So if you have Fy and Fx, so
Okay.
they have two components of your float. If you only have Fy,
Mhm.
B is the correct value, the correct topology.
What is B? Okay, log
Figure B.
What is A? First of all, let's just start A.
Yeah, yeah. So this shows what the problem is.
We have a cube. We have
We have
a
a square shape.
square shape.
Yeah.
We are putting this force F. What are the fixed points of it? This is the fixed point.
Yeah, these points at the bottom are fixed. These are fixed in Y, and this last one is fixed in both X and Y.
The last one is.
No, yeah, this one.
We writing version. So, start from right. Okay. So this one is fixed in both. Like we are like this is it, and what is it? We are like forcing. If we are doing this tablet, what would it be?
So yeah, so there will be rollers here that won't let you go up,
Uh-huh.
but they will let you go like this.
Ah,
And
okay.
then you have something here that's just fixed. So when you push something, they can deform in this direction. They can't.
Oh, deform. Yeah, I'm saying if it is fixed, there is what is the point of the other two rollers, right?
Yeah, yeah, it won't be fully constrained.
All right. Okay.
Anyways, so if theta,
So what is this now?
I'll explain. So if theta is the angle of the load.
Okay.
If theta is 0, this is the
Like
topology. Yeah.
vertical.
Yeah, this is the optimal topology, right?
Oh,
If you're just putting a force down, you just put a blob of material there, you're fine.
here you feel like this cube, this square with this.
Yeah, that's the amount of it. So volume fraction is 0.3.
All right.
This will be the shape that you'll get.
Okay.
If you even have a slight
But
theta-
wait a second. But if you fill it with this B,
Mhm.
there will be no point of contact with like the corners.
Yes, but if your load is only downwards, you're
Ah,
still
okay.
in balance.
Yes. Okay.
That's
okay.
exactly the point, right?
Oh, now that's why, because we have a zero, a
Even if you
small
have a
theta,
yes,
we
a
need to have
tiny
connection
data, you
with.
need to connect. But from a generative model's
Ah.
perspective, these are very similar images. Like statistically, they're similar.
Mass difference is zero.
Mass difference is 0, and also
Yeah.
the shape, the looks.
I mean, yes.
Statistically, they're similar.
Yes.
So we need to somehow make it robust to these things.
Mm-hmm.
And the way we propose to do it is we can just do a few steps of direct optimization.
Yeah. Okay.
Right? That's a very simple solution.
Like
So
again, like a bi-level method.
it's kind of like a bi-level, but here is like pretty much not even bi-level. It's like warm starting.
Okay.
Yeah. So the point is,
Dude, you can do an optimization on this ugly shape.
well, this ugly shape is actually the threshold of diversion.
Uh-huh.
There is like smooth, like non-zero values in the middle.
Mm-hmm.
That's why a few steps of optimization actually can resolve the features.
Okay.
Because what the model predicts is more like these. Like
Yeah.
they're kind of, like,
They have a small gap.
they have like some smoothness everywhere.
So to fix it from this to this, do you need to have a look at the shape, or your optimization method
yeah,
can
the optimization method sees this.
finds those
Yeah,
points?
it quickly resolves the features where there's uncertainty.
Oh, that's great.
Yeah, so it lets you do fewer, like it lets you do basically very little optimization, and you get like very good
I
solutions.
see.
So that's the whole thing put together, like all of it in one place. So you have this kind of architecture, this kind of approach. What do we do here? Again, this is like a conference work is limited results, and there's not much in terms of like.
One more time, like similar to the previous research we did. This, which part of this problem was yours, and the layering we talked, the architecture?
All the architectures there.
But this question that we want to come up with a topology that works for a
This is a question that has existed.
that is exists.
Yeah. Minimum compliance
Minimum.
topology optimization is very common.
What you gave was the approach to solve it. That was
Using deep learning such that it can be any resolution and shape.
nobody else used deep learning before.
No, people use deep learning before.
Uh
It's just that it's not applicable to like different shapes
huh.
and
Different shapes.
different resolutions,
I
and
see.
3D.
And 3D. All right.
It's not scalable basically.
Mm-hmm.
Like because it's convolution, it's not easy to scale it in 3D.
Mm-hmm.
It becomes very expensive computationally.
Okay.
Yeah. Anyways, so first thing is we have a data set and solver. I'm showing you a few examples of the stuff in the data set. But yeah, we generated a large number of.
New challenging data set. You created.
Yeah, we created a data set of these shapes.
What was like? That's actually great for other researchers.
Yeah,
right?
exactly. This is publicly released, and also our solver. So we have multiple resolutions in the data set. We have multiple domain shapes, specifically 7.
You generated them using your model.
Using a solver, using like a traditional optimizer
Oh, okay. You use the traditional
to
optimizer
get the data so that you can train a model to replace
Train
the
a-
optimizer.
to replace the optimizer.
Yes,
But these shapes here are produced by
an actual conventional optimizer.
conventional.
Yeah, we recreated the conventional
Did you-
optimizer with a faster solver,
Ah, okay.
so that we could generate a lot of data in a reasonable time.
Mm-hmm.
Because existing solvers for 3D take like hours to solve.
Okay.
We came up with this GPU solver because nobody has a public GPU solver. We don't have access to it.
I see.
So we have a larger number of boundary conditions and different domain shapes, 7 different
Mhm.
domain shapes, 120 different boundary conditions. And just to put it in context,
So multiple domain shapes 7. It used to be just one.
used to be just one.
And diverse boundary conditions.
Yeah. 120 different boundary conditions.
Okay.
Not load, but just where fixed points.
Fixed
different
points.
combination, 120 different
What
combinations.
number it used to be? Was it used?
Yeah, we'll get to it. Yeah, so this is existing data sets compared to ours.
Dude, you're just dominating them.
Yeah, because people don't have fast solvers, and we created this fast solver, and we
Yeah.
made it public. We released the code, so people can generate more data. Hopefully, in the
Mm.
future, we'll have a lot more data, and we can train
All
a
of
larger
them will
model.
cite you.
Yeah, and everybody who uses the data set or
Yeah.
the solver will cite us. Yeah.
Mm. I like about is that you are giving other people like a
We always do
lift
this.
for
Same
doing
thing with the linkages. We
Mm.
created the largest linkage, 100 million linkage mechanisms, and we created a fast solver, differentiable solver, everything. We put it public. You can use it.
It's really nice.
Yeah, we release all these publicly because the point is, if this is an interesting direction, it shouldn't be just us doing it. It
That's
should be
very
other people
important.
doing it.
Actually, that's one of my like concerns with doing works with companies is that they don't give their
Yeah, they don't publish.
they don't publicly give their data.
But OpenAI used to be like open and
Uh-huh.
actually publish their work in code and data.
Mm-hmm.
Now they're not because
Yeah.
there's money now.
Now they're rivals.
Now
Yeah.
they're closed AI.
Yeah.
Yeah.
Closed OpenAI.
Yeah,
All right.
closed OpenAI.
No, the thing is that, like, I am recently reading, trying to work with these companies. They have data sets, first
They
of
have
all.
massive data sets.
They don't
Huge
want
data
to
sets.
publish.
They never want to release that data.
Then, but they still want
It's
to.
competitive advantage.
Yeah. They still want to give some papers on them, some research result on them.
Mhm. They use.
But
they-
okay, the story is that we have this hidden data set, we did some algorithm on it, and it worked for us. What other people should do about what are the things for other people
Yeah.
to do for you?
So there's a bunch of research on how you can like release data without actually giving your actual data to people.
Mm.
That's Kava's research. In differential
Privacy, yeah, okay.
That you can talk to him about that.
It
stuff.
really helps replicability of science or whatever.
Yeah, I think it's very important to release your data, your code, and everything because then people can easily replicate. And that's the thing.
Yeah.
If you're doing work in software and computational work,
Mm.
it's easy to replicate. If you don't provide code, I'm always a little bit sussed out. If I
Yeah.
see something that people don't release their code and data, I don't know if I should trust the results.
Yes, that's true. Actually, let me show you. I was reading this paper from Airbnb.
Yeah.
I got into recommender systems. So they have this consumer model. First of all, they are doing the research. The only bad thing is that they cannot share the data.
Mhm.
So they say how we present these like pins of location and everything matters on the purchase, and they're doing a research on this. Why can't? Oh, okay. And then they have these graphs how user behave, but at the end of the paper, to be honest, they give an algorithm to improve their performance. They don't give you anything about user behavior. Okay, how another person can use this paper is a big question. Like, who are you helping with this?
Yeah.
It's just a bragging. We did this algorithm to our data set and it is working good for us.
I think for them, the main motivation behind publishing this is to get other researchers in the field to start working on this, so they can use their research in their actual work.
But
It's to get, like, free
even if
stuff.
other researchers start to work on this stuff, they don't have access to their data.
Well, if they get a grant from them.
Yes, that's like I am also trying to get a grant from them, and we need to sign NDAs and.
Yeah. So you'll publish something,
Mm-hmm.
you won't publish the actual thing.
Yeah,
Yeah, they do this all the time.
that's
Because
it.
academic work is cheaper than if they had to hire an entire team of researchers.
Sorry, what did you say?
Like, doing research in academia is cheaper for them.
Mm-hmm.
Because if they wanted to do a whole direction of research,
Oh,
they'd have to hire a manager, he would have to hire scientists, and they would have to do all this. It's a lot of money.
yes.
They can start things off with the academia and see if it works out, and if it is, then they'll do it in the real world. Like, they will actually do it.
Yeah,
Yeah, so they're basically, using their position.
I see. Yeah. Well, they have.
It's a
good data.
strategic choice they make.
Well, kind of as a researcher, I like to work with their data, something real.
Mhm.
Was it the same for you with IBM?
No, not with IBM, but when I worked with Lincoln Laboratory, that they couldn't give me any real data, even after having a grant and stuff,
Uh huh.
because it's classified, like this military stuff.
Oh, okay.
But I would get some form of feedback, like,
Oh.
what you did, we tried it on this and that. And it's
I
like,
see.
you know what I mean?
Yeah, yeah.
You get that feedback basically, but at least you get that feedback. But like, I think in the case of eBay and things like that, it's not sensitive. It's not that sensitive, so they may give you access to actual data.
Yeah, they may give me, but they won't let me to give it to other people.
Yeah, they won't let you publicly release the data.
Yes.
Like what we do, we release it, and this has always been the case. Is like we
But
try
I
to-
really like that, like because this thing you are giving other people something to work with.
Yeah, I'm giving people like, hey, this is a challenging thing. Try to solve.
That exactly. This is like something other people can use. You produced something for other people.
Yeah, we always do
Yeah.
this, by the way. Like in our work, in our lab, we try to always release data
That's nice.
and solve or whatever we can do to make more data happen.
Because like the Airbnb paper is actually what you said. They are like saying, "Oh, we are good. We are doing something here. Do you want to join us?" Like
Yeah, that's literally what that is.
that paper has no use for other people.
Sometimes companies release data.
Yeah, Expedia did, but
Like in our world, the Autodesk released
Mhm.
a bunch of like cat data.
okay,
Yeah. Sometimes they release it.
I see.
Sometimes it's like they don't care about the data itself that much. The data itself doesn't have value.
Mhm.
It's a very hard problem, so they want other people working on it to get the methodology going forward. Yeah.
Interesting. Good that okay. You want to maybe lecture?
Yeah.
That's
So-
actually a massive difference, by the way. You can
Yeah, for
see.
most things, yeah, it's a big difference in terms of like increased number.
What is configurator?
This is boundary
boundary
conditions.
conditions.
Yeah.
Alright.
So you can see they usually have like 10 different boundary conditions they train on.
That's massive
Yeah.
difference. And then total elements.
In billions, like the total number of data, like density values. Like if you put all the element
the
counts.
finite.
Yeah, it's
thing.
sort of like the if in LLM world the number
Well,
of
this
tokens.
shows a big change. How do you say that it was not impressive?
It's because this was the solver that
Okay.
we made. So the solver is nothing new. It's
Mm.
it's the same. It's that method has existed.
Mm.
We just so it was engineering work only.
Okay.
It was like, oh, we made the computation, so we optimized the code.
Mm.
We made a GPU enabled solver so that it can run things on the GPUs is faster,
Okay.
etc. That's just
You
engineering work.
improved the technology.
Yeah, we improved the technology. It was very practical work. Like
Yeah.
if I was working for Apple and I did that, that would be one thing,
I see.
right? Like, but it's not like scientifically interesting.
All right.
Yeah. So when it comes to
And
performance,
how many domain shapes? It was like 120.
120.
Where is
Well,
it?
configuration is 120. Domain shapes is 7.
Yeah.
Yeah.
Okay. Like what are the domain shapes?
Different
I know. What
different
are
shapes.
the 7 ones that you worked with?
Uh,
Sphere is weird.
No. They're all rectangular prisms, but like rectangular prisms with different aspect ratios.
Oh, with like aspect ratio is the.
Yeah. It's not like different, like very weird shapes.
Okay.
Yeah, it's all rectangular prisms.
All right.
Yeah. I mean, we are actually building a data set of fully random everything.
Fully random everything.
Everything. So it's just like the number of data points is the number of configurations. The number of data points is the number of shapes. The number of data points is the number. So it's like a fully random everything, and we've generated so far around 4 million of them. 4 million. 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 4 million and we're training like a model.
Who can use those data?
We can.
Oh, you can.
Yeah, we're training a model that is like in a few tens of billions of parameters
Mm.
for this kind of thing.
Yeah.
And we're building.
I have no intuition about these numbers.
And yeah, it's very big. It's
Okay.
hard. Like, people don't have the hardware to do
Yeah.
it most of the time. And we're also building like generalizable to different physics.
Mm.
The actual problem that would be impressive to solve. The one we talked
Physics.
about when you mix physics.
Oh, okay.
So we're
I
building.
thought you addressed that in this work.
No, this one we stick to minimum compliance,
Oh, okay.
right? Proof of concept here.
I see.
That we're working on that one where it's like a general thing. That's like if we get that done, that is very, very important, like groundbreaking.
Yeah, that is actually, right now it should be a fight between two engineering teams. I want this heat thing, and the other one's, oh, I want that.
No, so with what we're doing is say, give me PDE.
Mm.
I don't care what it is.
I see.
Give me your PDE and I will do
Mm.
it.
Mm.
That's like very general,
Yeah.
right? Because it's not like I want heat equation or I want a linear elasticity. I want everything. I don't care.
Mm.
Tell me what your equation is in math, in pure math.
Mm.
I will figure out the rest. That's what we're doing now.
I see. That's crazy.
Yeah, that's the hard problem.
Mm.
So like, that's why I said like the main.
But
actual-
right now you are also giving it just a PD, right?
Yeah, we're just. This is one though. This is one PDE. Like, he can't handle anything different.
Oh, you don't have a system of equations.
Yeah, I'm saying arbitrary, like anything he give me.
Well, how do you have anything for two PDs?
Again, I'm saying we're building something for whatever.
I'm saying already. Do you have anything for two PDs?
No, right now with the we have like single PDE,
Mm-hmm.
and we do. Yeah, arbitrary shape at least.
What is the next? I mean, the next step is like anything.
Yeah.
But what is the next problem that is easy and you are still like one step ahead?
Yeah. So this would be the one step ahead thing would be buckling, for example.
Buckling. What is
Same thing. So same as the elasticity, but sometimes when you deform something,
Uh-huh.
for example, let's say you're pushing something down.
Okay.
Have you seen like where like there's one point that breaks down like that, like very quickly?
Okay.
It buckles. It goes from elastic to plastic
Okay.
deformation. Finding the buckling points, when you change your shape,
Mm.
you have to solve an optimization problem to find where the buckling point is,
Okay.
and then you can solve for the optimization step. Because and then now every time you take one step of the optimization, shape changes. Now you need to find the buckling point again.
Okay.
It's like so much. It takes current solvers take like a day to solve this one at a time. Yeah, we think we can get that down to a few seconds.
Jeez. All
Yeah.
right. Okay.
Yeah, and there's like startups in this field of topology optimization, like many of them. Some of them have raised like tens of millions of dollars
Tens of millions.
to do machine learning for this kind of problem.
That's great, dude. Machine learning changed the world in ways that I haven't heard about.
Yeah, I mean everybody's like, the thing is you find any niche and people are doing something there.
Mm.
Anyways, like performance-wise, like these are some of the like visual results of like what it looks like.
10 is what is 10?
10 steps of direct optimization.
10 steps of direct optimization.
Yeah. So like, okay, just to put it in context, the ground truth, which is generated from the optimizer,
Mm-hmm.
it requires 500 steps.
Okay.
So
500.
10 or 5 or 10 is like 2 orders of magnitude.
Mm.
Yeah, that's what the point is. 2 orders of magnitude less.
Less.
Yeah.
But it is producing the same thing.
Almost. So
Um,
you see when you don't run the optimizer, you see these holes and stuff.
Uh-huh.
They get healed very quickly by a few steps.
Okay. Okay.
And also the reason I'm doing this cut thing
But
is I
ground
want you to
truth-
see the internal features that are also changing.
I see. Ground truth should not have holes, but these are.
Yeah, this is like what the optimizer produced,
Mhm.
and this is what the model produced. So it's
Uh-huh.
not correct, quite correct.
Mhm.
But then because the density fields are continuous and
Mhm.
it has like uncertainty information, it very quickly resolves
I see.
with a few steps of optimization.
This one has almost no hole. Exactly.
Yeah.
How long does this take?
We'll get to the first time.
Let me see other shapes.
You see, there's like some
Yeah.
holes. They
Why?
go away.
Why usually the first one has a lot of holes?
Because that's the raw one. There's no optimization run on it.
I'm wondering why it leaves some holes.
Well, these are not holes because you threshold them. It gives you a density field, like it's
Uh-huh.
continuous, and you say anything above 0.5 is considered material.
Okay.
Yeah, that's why
Okay.
it's hard to visualize the
Okay.
3D
Okay.
fields,
Okay.
right?
Okay.
That's why we don't do it.
I see.
It's very hard to visualize that.
All right. Go ahead.
Anyways, performance, the metrics we use is compliance error and percentage and volume fraction error. What that means is compliance error is basically what is the difference between the compliance, that stiffness, the
Mhm.
objective, compared to if we ran the optimizer.
All right.
And you can see it's like
What is
0.3%
VFE?
Volume fraction error.
Volume.
And what that is if I gave you the volume fraction goal I had, how far off are you from that?
I see. Okay.
So it's like 0.3% after 10 steps of optimization, 0.5% after 5 steps of optimization, which is basically like from an engineering perspective, is more or less just same as the solver.
Same as the solver.
It's like half a
Yeah.
percent.
Yeah. You should. We
Half
should
a
have
percent
the
is not.
solver for
Yeah,
comparison.
so this is compared to the solver.
Oh, this
half a
is
percent
10 is
off.
the.
It's half a percent worse than the solver,
All right.
and it's 0.3% worse than the solver.
Percent, which
Yeah.
is okay. Very.
Yeah, which is very small, right? Like from a practical perspective, that's nothing.
Okay.
And these similar trends with volume fraction errors is fairly low.
Yeah, it is low.
Yeah, so basically we're saying like at least for this limited case study, we can do it.
Somebody's coming.
Yeah, at least for this limited case study, we can do
Yeah.
it.
All right.
And here I'm just visualizing how the distribution changes. The
Mhm.
distribution of compliance error as I do the direct optimization. So like it narrows down the error to zero.
Zero.
almost.
It's zero. By the way. All right.
You have some negative ones too, which is the interesting thing. Where it does better than this.
Better than the.
Few times, like not
Yeah.
they're not common, but it does happen. And you see some of these go away. The reason some of these go away is because they actually are using more material.
Uh-huh.
So when the solver gets rid of those extra materials, actually it gets
Better.
worse. Yeah,
Oh,
but like
worse.
at the very top, you still see some of them are even with the same like volume usage, they're still better.
Mhm.
Yeah,
But it has looks like some famous curves.
it's kind of like a normal distribution.
It is not no. It's kind of a skewed way.
Yeah, it's kind of, but like it's almost like a normal distribution.
Yeah.
Not a perfect Gaussian way. So efficiency and speed, well, speed up wise, going for the inference time,
What is acceleration?
like the speed up,
Mm-hmm.
how much faster we get.
99%.
But that's if you didn't do any direct optimization.
Okay.
99.95%. But with direct optimization, it's 93% faster.
That's crazy.
Yeah, and just to demonstrate this, sometimes in practical applications, what you do is you have set boundary conditions, but
Mhm.
your load direction can be anything depending on your design. So you're designing your system, and you're trying to figure out which load direction gives you what shape. So you're
What is a low direction?
the direction in which you apply the force.
Okay.
Say you know
Load direction.
Yeah, load.
Okay. Okay.
So what you know where the fixed points are,
Mm.
but you have freedom on which direction you apply your load,
Uh-huh.
and you're trying to figure out which one leads to a better topology, like less compliance and also the shape. You know. So you're rapidly changing the direction of your load and trying to find the optimal topology, and you want to see all of them.
For each force, you are creating an optimal topology.
Yeah. So, but you want to quickly see what that looks like for different forces, different directions of load.
Oh, okay. So you design it for one force, and then you want to
No.
see
You don't
reaction.
design it. You know the boundary conditions, and you know where you want to apply the load.
Mhm.
But you have freedom on which direction you apply
Direction.
the load. So you want to see which of these leads to a better optimal topology.
What do you mean better? Okay, this sentence
two
better,
considerations.
better optimal.
Yeah.
It doesn't make sense to have a better optimal topology.
No, but the problem is changing.
Yes.
Yeah. So the force direction changes the.
So okay, the thing is that is it true? Like the point of the force is constant, but the direction changes.
Yeah.
So for example, let's assume I designed it for the vertical force down.
Yeah.
Am I gonna check if this topology is working good for other directions of force?
No.
No.
You're saying I want the optimal topology,
Mm-hmm.
but I am free to change the direction of the load.
Mm-hmm.
And depending on which direction of load I apply, I'm going to get a different optimal topology,
Yes.
right? And now I want to see all these different optimal topologies so
Mhm.
that I know, for example, which one is better for manufacturability. Like which one's easier to make.
Okay.
Or which one has the lower compliance. like which direction of load will allow me.
Isn't compliance defined for that direction of force?
Yeah, yeah, yeah. But what I'm saying is I'm free to change the location or the direction of the force, right?
Yes.
Which direction of force gives me the possibility to have a more stiff structure, right? Like if you're fixed in X here,
But okay,
and you
maybe-
apply a direction in X, you're going to be very stiff.
Mm.
But if you apply slightly in Y, you're not going to be stiff.
Yes.
You know what I mean?
Yes.
You want to test different loads and see which one gives you a better performance.
That is robust to different directions.
No, what's the difference? Okay,
No?
let's just say this. In this example, you're trying to find optimal topology for different load directions.
Yes. Okay. So
Yeah.
it's like expectation. If you had like a density over force direction,
Yeah.
you want to optimize for the expected.
Or you want to see what each direction results in. Like, what's the optimal topology look like for each direction?
Well, that we have. Optimal, like
Yeah.
by so far we have
What I'm saying is,
optimal.
all I'm trying to show here is like how much faster it is and how much more information you can gain
Yeah.
using the AI compared to if you were to run.
Why? Because you created this fast method.
Yeah. So this is just
So
a
wait a
demonstration.
second, no. You created this fast method that previously we didn't have the option to come. Okay, consider 10 directions for force because it took us like a lot of time.
Yeah.
Now, with the faster
You
way,
can quickly see.
we can generate the solution to 10 direction of force,
Mhm.
and then we can pick one of these 10s.
Yes.
But which one of these 10 do you want to pick?
Depends on two things. One is like the most important thing usually is which one is easier to manufacture.
Oh, okay.
Yeah, that's one of the things. Also, which one is more stiff? Like which direction of load leads to a more stiff optimal topology?
But stiffness of a topology, are you saying is it independent of the?
It's not.
It's not
dependent on the load, but you don't know what the actual compliance of the optimal topology is for each load direction.
Yeah.
So you don't have that information.
So it is about robustness. to
Yes,
other-
yeah,
all right.
yes.
Okay.
So here I'm just showing you how much faster it is to flip around the forces and get.
Is it
solutions.
possible that like you design a like very stiff thing for one force and it's very fragile?
Yes,
Oh, actually, it was the example you had at the beginning that it didn't have. All right.
it is. That's
Yeah.
very possible.
Yeah.
Yeah, so there's ways if you're trying to build robustness in different directions, what you would do is you have to solve all the problems separately and then try to find the combined best solution.
Yes.
Yeah, which also basically means you need to run a lot of these topology optimizations.
Yeah.
Here I'm just showing you this is 4 times
Or
sped up.
maybe
Yeah.
minimum, like what is it called? Pessimistic. What is the worst case
Yeah,
situation?
yeah, yeah. So you
Right.
can, basically here I'm just going to show you what traditional optimizer on the right
Mhm.
does, and this is 4 times sped up,
Mm-hmm.
and this is our model in real time.
Mm-hmm.
And just look at the load, the purple arrow.
Where is the purple arrow?
It's here.
They are not the same though.
Yeah, because the videos are like as soon as I hit play, it will be.
Okay. Okay.
And we're gonna have a counter next to each of these and how many problems have been solved.
All right.
1 on this side, and this is real time. That's 4 times sped up. That's still on 2. This is
So
on
you
4.
already solved for 5 directions.
And that's 4 times sped up, by the way.
Oh, okay.
Yeah, it's like significant. Like this, I mean, the point is made. I think very
Yeah.
quickly, right?
Yeah. Okay.
So
now
the value
actually
proposition-
now you're changing faster. This one is a lot.
Yeah. This is because again, like it's very slow. The
It's
solve is
also
very slow.
interesting how shape changes based on different direction of the.
Yeah, because I mean that's
Force.
yeah. I told you one direction you can have a topology from in one direction, and it's not going to be good for another.
It's not.
Yeah. Even if it's the same location where the load is applied.
So this is actually we needed the time efficiency.
No, time efficiency is very important
Yes.
in real world design. Like when you're trying to
Yes.
when you do
We
rapid
can, I
design.
cannot just design for one direction. I have.
So rapid design actually is where you
Yeah.
have to do this. Yeah. So again, like there's a lot of value propositions here. Anyways,
Wait a second. One question: does adding material to one part
yeah.
decrease the stiffness in any way, or it doesn't?
Adding material. What do you mean?
Like if I add, for example,
If you add extra stuff to
Yeah.
an existing topology, Well, it won't make it worse.
It won't make it worse.
No, of course not.
Of course. So maybe we can kind of average all of
That's
this.
one of the ways people do it for
I see.
robustness. Is they
Mm.
average out,
And what will be the shape
or
of
they
it?
take the union of them and then
Union of them, yeah.
union of them, but then the volume total will not be met.
It should be divided by
So
the
what they
number.
will do is then they say, okay, let's run them on lower volume fractions
Uh-huh.
and then union them until
Yes.
we get the right volume total.
Yes.
That's one of the ways.
Well, how will
That's a bi-level approach.
That's a by-level.
Yeah.
How will the final shape look like if we do that? Do you have?
I don't have any example.
Okay.
Anyways, I mean the
I
conclusion.
don't like it if it is like a full bar at the end. That will be.
Well, that doesn't meet the volume.
That
It
doesn't-
will be weird shape.
I
It will
see.
be.
It will be weird shape.
100% will be.
Ah,
weird
okay.
shape. Yeah. So what we did in the paper, in this conference presentation and conference paper, it was we brought in a domain adaptive resolution free approach, which didn't exist before. So
Domain
different domain
adaptive.
shapes and it created a resolution.
By domain shape, you mean aspects because.
Yeah, for now it's aspect ratio, but the method can be applied to any shape, right? The methodology that we introduced
okay,
is not
okay.
limited. It's just that our data is limited.
All right.
Okay, we didn't have enough time to get insane numbers of like different shapes in data, right?
Okay.
If
Have
you
you
could-
tried it on
Yeah,
another
so
shape?
I told you that we have around 4 million now of different shapes,
I
like
see.
fully random everything. So yeah, we're trying that. There's some.
Wait, no. You said that governing equation was one
yeah,
way
one.
to
This,
one
this
direction.
is also one. The governing equation doesn't change amongst these. They're all linear.
Do you had tried to do it for another shape?
We are working other shape.
Domain shape. Domain.
Yeah, domain shapes are already changing here.
Yeah, but like a cool shape, like a ball.
Well, ball is not that hard to do, but
Really?
yeah, we've tried it on different shapes.
All right. Okay.
Like usually it's like a shape of a wrench or a sort of
Ah.
connecting material, like or like a
Mm.
bracket or something.
I see.
Yeah,
Domain
not like a
adaptive.
ball, but like you could try to run like maybe internals of a like a sports ball or something.
I
You
see.
could try that, but yeah.
This is our
So-
beginning.
Yeah, we're just reviewing. This is like
I see.
the conclusion slides. Yeah, so point cloud representation. We have the convolution free and scalable, so we can have very
What do you
fast.
mean convolution free?
So we're not using convolution neural networks.
Okay.
And the issue of them being limited to domains and resolutions.
No cost, the scalability.
To high fidelity. The model that we introduced.
What is
the
high fidelity?
high resolution, very, very,
Ah,
very
okay.
high resolution. You can train the same model for very, very high resolution
Ah,
without
okay.
actually requiring a bigger GPU.
Okay.
It's very scalable.
An order of
And
magnitude. Yes, we
acceleration.
just saw it.
Precision through deep generative optimization. What that is basically combining generative models with optimization. So it's just like demonstrating that that's an important thing for robustness.
Alright.
And at the end, I just wanted to like say,
I have convinced you of these facts.
yeah, I have convinced you that TO is a great platform for proof of concept.
TO what it stands for?
Topology optimization.
Topology optimization.
The future of research in this direction lies with generalizability to domains, resolutions, and multi-physics
Yeah.
foundation models. So you need to build these foundation
Mhm.
models. And deep generative optimization is a promising platform for precision. Basically combining optimization with deep generative models.
That actually was a really interesting thing that you come up with like bisect data and then
Yeah.
it
So I
gives
think
you a very good starting
it gives you
point.
robustness
Yeah.
when you have the optimization.
Yeah.
Because without the optimization in engineering design applications, again, statistical models are great, but you
Mhm.
need to be robust.
Mhm.
Because precise, it's a very precision, it's highly precise thing to do. You can't just, again, like small amount of change can lead to a huge outcome
Mhm.
difference. And also data is key.
That should be my thesis proposal.
Yeah, data is the most important thing because if you want to train these models on a very general thing, you need a whole lot of data. So if we're going to see GPT levels of performance and
What does
precision,
GPT stand for? Generative
I think it was,
pathology.
I don't remember what it was standing for. Oh, shit. Okay.
Data-
Generative pre-trained model or something?
Pre-trained. Alright, sounds
I
good.
don't. I haven't.
We are yet to see the GPT of precision engineering.
Yeah.
I hate this term, GPT of precision engineering. That's 4 words next to each other.
Generative pre-trained transformer.
Alright.
Yeah.
And data is key success. That's what.
So
I'm
we need
saying all
a
the
lot
time.
of data
Mhm.
to be able to do like GPT levels of things. Like if you want to train a model that has hundreds of billions of parameters, you need a whole lot of data.
Hmm.
That's why we released the
Where
solver.
do you get your data from?
Yes, that's why we released the solver so everybody can run it
And give you the data.
Yeah, or combine the data. You know?
It's a win-win game here.
Yeah, and then at the end I had the link for people to go get the code and data and do their thing.
Is it also a result of your work, or is it just?
No, this is just a demonstration of running the solver. It's our solver.
Okay.
To solve this with traditional optimizers takes like 3-4 hours. Our optimizer does this in like 4 minutes.
All right.
Yeah,
That was really cool. Thank you.
of course.
Any final comments
No?
for our armchair theorist fans?
Yeah, not really, but
All right. Thanks a lot. It was amazing.
thank you.
I mean, you put a lot of. Okay, he didn't do it for our podcast, but like, it is his PhD in general, and like,
I have more presentations.
yeah, he put a lot of energy. Honestly, as somebody who barely draw graphs, these like 3D stuffs, and they are really cool. He also built a website for the.
Yeah, we have demo like live demos for a lot of things.
That's really cool. It's all on you. You didn't have any assistant.
No, I did it all. Yeah.
These people are bad for
They set a bad
society.
precedent. Yeah.
Uh-huh.
They set a bad precedent.
No, I mean it's just you bring the standards up, and that sucks.
Dude, you don't even know what other people are doing.
What are they doing?
Some other departments are crazy.
What
Like the pure science departments,
Mm-hmm.
like physics, math, chemistry.
Uh-huh.
They're crazy. They work all the time.
Really?
Yeah.
And they produce
They have like
nothing.
no life. Yeah. I mean, they can produce something.
Yeah.
But like they work because a lot of them are experimental work. They have to go into a physical
Oh yeah.
lab.
Yeah, yeah.
And they have to do it all the time. They spend like 12 hours every day there.
Well-
Some of them sleep in the lab. Some of them have
Guys, if you are studying, like you are interested in pursuing PhD, these are good advice for you. You can consider, like, yeah, you may like physics, but you may not like studying, sleeping in your lab.
Yeah, if you're doing experimental work, people like literally buy.
Yeah, people hear Albert Einstein and they say, oh, well, I want to be Albert Einstein.
Well, he was doing theoretical work.
He was doing theoretical. I am saying just sometimes you like something, but you don't know all about it. So
Yeah.
I'm not gonna sleep in a bag. Not a bag. What was that? Lab.
Yeah, they sleep on a sleeping bag in the lab.
In
or,
the lab.
or something. Yeah.
Dude.
It's crazy, but yeah.
People who go do animal documentaries, those are the real ones.
Yeah. Sleep in the jungle.
Yeah,
They
Maybe.
have a support truck.
they have. Actually, one of the documentaries on Netflix was that they were like 5 machine and they were covering.
It's even they should have backups like if one of the cars breaks down.
Yeah, and like every I don't know 1 month or once a week they came back to the because they don't take showers.
Yeah.
They go back like to the camp they have and like act like normal human beings for a while, for a day or two, and then they go. Anyways, thanks a lot. 3 hours 21 minutes 48
Is this a
seconds.
record? Or?
This is the record, I guess. Yeah. All right. Thanks a lot. It was exciting. I got excited a lot of times. Thank you. Bye.